Hello, everyone. Are we live? Can we have a full screen here? We're good? Hello, everyone. Very happy to welcome you to the second edition of the SHARP workshop at CVPR 2021. So the SHARP workshop is about recovery of shapes, 3D shapes. We have challenges, we have special talks, plenary talks. I'm very happy to host the event. We'll have some co-organizers joining shortly, I hope. So my name is Jamila Awada. I'm a researcher and professor at the University of Luxembourg at the S&T Center. And this event and workshop is co-organized by the University of Luxembourg, S&T, and also sponsored by Artec 3D, who are an industrial partner. So today we have an exciting program. We have two exceptional plenary talks. I see Adrien already there. Hi, Adrien. And in the second session, we'll talk more about the challenges. We'll present them, give room to the finalists to present their works. And of course, the very exciting moment, we'll tell you who will share the 9,000 euros as a prize for this challenge. We have three challenges, in fact, so this will have to be split. We'll have Ksenia Cherenkova, who is co-chair of this workshop, announcing the prize, to whom the prize will go. And Ksenia is co-chair, and she's also a participant, so she knows the challenge very well. And without more delays, we'll go up. I think there is an automatic thing happening here. So we'll go with the plenary talks. We'll start with Adrien Bartoli. Adrien is already here. So I'll take a couple of minutes to introduce Adrien. It's a huge pleasure to have you with us to open our workshop today. So I'll introduce you very quickly. Adrien is professor at Université Clermont-Auvergne in France. He's leading the NCOV research group, where his main research interests and contributions are on deformable 3D reconstruction in computer vision and computer-aided diagnosis and surgery. Adrien is also associate editor for the International Journal of Computer Vision and for the Journal of Artificial Intelligence Research. And Adrien is very well known. He has served and still is serving the community as area chair for different conferences, major conferences. And I'll give you the floor, Adrien. We don't hear you. I don't know if you have the mic on. So Adrien.
Yeah, you should be able to hear me now. Can you?
Excellent. So Adrien will talk to us today about reconstructing deformable 3D surfaces from monocular video using geometry. The floor is yours, Adrien.
Thank you. So I'm going to share my screen. Not sure I can. So I think you may have to allow me to share my screen actually, because the share menu is great into this WebEx application. Okay, now it's accessible. So can you see my my presentation?
It is the presenter view, if you can.
Yeah, well, so I'll stop sharing, but I don't know when perhaps you can tell me, but screen two, right? Perhaps I should do that.
Yeah, this is fine.
Yes.
All right, excellent, thanks. Well, thank you very much, Jamila and the other organizers for the invitation to speak to this workshop. This is very exciting, and well, I'll start. And as you said, so I'm going to speak about 3D reconstruction of deformable surfaces from an monocular video and using mostly geometric cues, a bit of deep learning still, as you'll see. And so I'm leading a research group which is named ENCO, that means endoscopy and computer vision. So we do computer vision with the as targets mainly computer-assisted surgery. So that's what we have in the background for our developed theories and systems. And so I'll talk about the methods and then show application in computer-guided surgery at the end of my talk, and you'll see how it's used on concrete examples. Right. So 3D reconstruction, as you know, which is also called inverse imaging, is about the task of converting several 2D images to a 3D model of the observed object or environment. So with pictures, we have a camera that films or take photographs of the environment. We can access digital images taken from this camera, and we reconstruct a model of the environment, which can be a point cloud, something very simple, and a model of the camera at the different time instance where it took the different pictures. And of course, this is just a mathematical model. This is not reality, and we can make the scene structure more complex by adding to the point cloud things like the topology, using the mesh, so which codes for the relationship between the different observed points. We can encode the appearance with a texture map. We can make it smooth to be able to access differential properties, and we can even complexify it even further. I will use differentiability a lot in this presentation, and also the appearance to be able to match the models to each other, to the images and across images. So there are mainly two approaches nowadays to reconstruction. Of course, the learning-based approach is gaining popularity. The idea is to learn the reconstruction function directly from data, and so we have this huge function represented by a network that maps the image data directly to the model of the reconstruction, so to the structure on the cameras. And by doing this, we sort of avoid the analysis, the explicit analysis of the images and what we call the visual cues that they contain. These visual cues, they are these cues from the images that tell us something about the 3D content which is observed in the images. So here with this approach, everything is contained implicitly into the weights of the network. But the other approach, which is older somehow, and which has been also used very successfully, which we could call the physics-based approach, is based on analysis, explicit analysis of the visual cues. And typically nowadays, this would be called the handcrafted approach, where we search the images for visual cues that tell us something about 3D. And probably one of the most successful visual cues is the visual motion. So where we observe the primitives, the motion of geometric primitives across images. And from this motion, we can infer 3D. And other well-known and successful visual cues are the shading, the occlusions, the blur, the silhouette, and the shadows, and there are more of them, probably more exotic, but these are the main ones. So I'm going to discuss this physics-based approach to 3D reconstruction mostly in this presentation, in the case where we have deformations. Classically, this has been studied a lot with the assumptions of rigidity. So This is the one-on structural motion approach, where if we can take multiple images of a rigid structure, something that doesn't change through time, we then have access to a whole theory, the theory of visual geometry, and its computational implementation, which is structural motion and SLAM to some extent, visual SLAM, and which is a very mature technology nowadays. So you can see an example from the literature on the right side of the screen. So I'm going to discuss this in the case where what we observe is not something which is rigid, something that doesn't change. It is something that evolves through time. And a very simple example, which I'm showing here, is a piece of paper which is deformed. And we take several images of this piece of paper. And so the shape is never the same through the images. So rather than searching for one shape as in structural motion, we here search for several shapes, one shape per image, and we have to recover all these shapes. So if we have n images, we have to find n shapes, still combining the visual cues from the n images. And I'm going to take the physics-based approach, and I'm going to use the visual motion approach. So that forms quite a recent problem compared to either the rigid structural motion and the other traditional visual cues from visions. And the main question we have to address here is how can we combine the different images, what priors we can exploit to replace somehow this very strong rigidity prior used in structural motion. So there are several types of such priors we can use, and the first one, which is a very natural one, is to put priors on the shape we want to reconstruct. And a natural one is the smoothness, of course, that the shape, if you look at one point on the shape, the other points close to it will be also close in space. And we can implement this mathematically with a constraint on the smoothness of the model that represents the shape. There are other possible constraints, of course, and I'm going to stick to smoothness for this discussion. Then there are priors we can put on the deformation that occurs in time across the different shapes, across the different observations. And I'm going to exploit smoothness and another important one, which is isometry and approximations of isometry, such as quasi-isometry, that tells us that when there is a deformation occurring to the surface, then the points stick together. If they're neighbors, they'll move together in space through time. And finally, there is a very important prior that we cannot always exploit, but sometimes we can. You'll see that in the medical application that I'll discuss, we can sort of exploit this template prior. And this prior tells us that we can have access to a model of the object in some reference configuration. And typically, reconstruction can consist of deforming this reference shape towards the target shape given the image data to guide the deformation. So in this case, when we have a template, the problem is called shape from template, the reconstruction problem. And there is an important result from the literature, which says that it's solvable from a single image only. I'll go through the details of why this holds. But the problem setup is this one, the one you can see on the screen. So you have a template. Again, this is the object we're interested in. Here, this piece of paper in some reference shape. Here, it's an easy case because the paper can be physically flattened. So as template, we can just take a flat plane. And the shape from template, the SFT process, takes this template and an input image and can output the 3D reconstruction of the object as seen from this input image. So the ability to solve from a single image only is a very nice property because it means we can solve in real time without relying on past images, past observations, and so we don't need tracking and these sorts of things to be able to recover from failure, for instance. So that's a nice property. In practice, the template is available from either a digital object model, which is a very common case. For instance, if you have a CAD model and if you 3D print the object, then of course you have the object model from the start. But other possibilities could be to scan the object using structural motion or structured light scanning if you just have access to the physical object, and then you can recover the template model to be used in SFT. This video shows an example of what we can achieve with the current state of the art in SFT. What we can see on the top is the digital model of this juice bottle, which was actually reconstructed from a 3D scanner. And these three sets in the video on the bottom of the screen show the input image from the left to the right, the input image, the computed depth map, and the textured 3D reconstruction on the right. So this runs in real time. This is joint work with my colleague Toby Collins. And as you can see here, we have access to this live 3D reconstruction, and it's not just the computation of a depth map. We have a completion mechanism for the hidden parts of the object. So if you look right now on the right of the screen, we can visualize the back of the objects, even though we never observe it in the actual image, which is because we sort of register the 3D model to the actual image. So we deform the whole model towards the actual image, and even the hidden parts are recovered in this process. In these results I'm showing, there is no deep learning. This is entirely based on modeling and physics-based reasoning. So the second case of 3D reconstruction, which is also very important, is the case where we don't have access to a template of the object. It could be, for instance, where we don't have prior information on the object, like we discover the object at runtime only, or in the case where the template is not constructible easily. So in this case, if we want to be able to do 3D reconstruction, we have to use multiple images, as in this example. So here we have three images of a piece of paper, and we're able, with this algorithm, to reconstruct the three observed 3D shapes. This is a very direct extension of structural motion to the deformable case, to the non-rigid case, and it's been called in the literature non-rigid structural motion, NRSFM. And we have been able to prove that it's solvable from at least two images, even though with two images only, we still have ambiguities that remain, but there are discrete ambiguities in the general case, and I will give you some details about it. This is not a technology nowadays, but the research is quite advanced, and there are solid theoretical results on what we can obtain from several images. So this is the layout of the rest of the presentation. I'm going to discuss FaveFrame template. So this example where we have a template and just one image as input from which we do reconstruction. Then the classical non-rigid structural motion. By classical, I mean non-deep learning approaches, so with physics-based reasoning. Then I'm going to discuss briefly a recent solution we came up with for the SFT problem using deep learning, which we call deep SFT. And finally, the application of these technologies to laparoscopy, which is a form of minimal invasive surgery. So we start with this SFT problem. So we have the template, the input image, still for an example on a piece of paper, and we want to do reconstruction on this piece of paper. And this is how the classical pipeline looks like. So we first match the input image to the template. For that, we use key point correspondences. Here I'm showing SIFT correspondences. Of course, there are miscorrespondences because this is based on local comparison in the scripture space. And of course, since several points look alike, there may be mismatches. So we have a local consistency check of these correspondences. Basically, we look at the correspondences and the neighboring points, and if they don't agree in terms of the displacement they have across from the template to the image, we sort of discard them because this indicates that they must be miscorrespondences. This removes a lot of miscorrespondences, not all of them, but a lot of them. So we have quite clean data from there. The next part is to do 3D reconstruction from there. But before that, we have a critical step, which is to upgrade these point correspondences to what's called ACEs, affine correspondences. So for that, we basically upgrade each point with its local differential structure represented by an affine transform. This affine transform, this encapsulates the local behavior of the optical flow basically between the template and the image. This is like the first order expansion of the optical flow around each point and can be represented by an ellipse on the images. So if you look at the content of the ellipses drawn on these two images, you can see by close inspection that the content is approximately the same. This upgrade is very important because, as we'll show, there is a computational procedure that can reconstruct each affine correspondence completely independently to 3D. And this is very important for robustness because it means we can do local 3D reconstruction without relying on the other correspondences, which of course may be wrong because of the matching process. So this is important because if you're familiar with structure for motion, you know that in structure for motion, a very essential component is the ability to do random sampling with RANSAC, for instance, to be able to be highly robust to mismatches. And the ability to do RANSAC is because we have global motion models for the whole image, like the fundamental matrix, the projection matrix, the trifocal tensor, etc. In the deformable case, all this breaks down completely. So the ability to be able to do robust reconstruction here involves being able to do very local reconstruction. So to be able to reconstruct from just one point. And I'm going to now discuss this, the theoretical foundation of how it's possible to do this very local reconstruction, this shape inference process. So I'm going to present this one-point reconstruction theory very briefly by giving an algebraic derivation. If you're interested in the details, this is of course provided in the papers, and this is based on Riemannian geometry. And then I'll speak about the extension of these to non-rigid structural motion. So when we have one point correspondence with the affine region around it across multiple images, but we don't have the template anymore. So in the case of SFT, we first have to start with the geometric model of the problem. So here we have the template on the left. Of course, the template here is a 2D template because the paper is something we can physically flatten, but the approach I'm presenting is trivially extendable to 3D objects, the ones we cannot flatten physically. On the right, you have the input image on the bottom, and on the top, we have the unknown surface that we want to reconstruct. So we're going to assume this surface is differentiable. Actually, we assume it's smooth, but we just need it to be twice differentiable. And we have this operator, capital Pi, which is the projection operator that takes a point in space in camera coordinates and projects it to the image space. And this is equivalent to just knowing the intrinsic parameters of the camera. So you can take this one for granted. In this figure, everything which is green is known. And so the arrow that goes between the template and the image represents the fact that we know the affine correspondences from the pipeline I've presented. And everything that is blue, the dark blue, is the part that are known and that we want to compute, in particular this 3D surface. So we start with this PQ point coordinates. So you can take these as the 2D coordinates of a point in the template and in the input images. Here, we're not using the affine part of the correspondence from the start. We'll introduce it shortly, but I just want to show you that if we don't use it, of course, the problem cannot be resolved. So we state our problem, find the 3D point capital Q in the 3D space, given the correspondence P to Q and the projection function capital pi. So our constraint is that if we take the 3D point and we project it to the image, of course, it lands exactly on the observed image point, small q. So capital pi applied to capital Q is small q. So can we solve this? Of course, we have to count simply the number of unknowns. We have x, y, z for the 3D points, and two constraints, which are the x, y constraints in the image, and of course, it's under constraints. We're short of one constraint, so that's an obvious reasoning. So let's build up with more constraints. We now introduce these local neighborhoods, as you can see with the small green circle in the templates, and introduce the fact that when we embed this template to the 3D surface, this local neighborhood should be preserved. That's this isometry constraint I was mentioning as prior at the start of the presentation. The isometry just means that we don't have local extension around the points on the surface. This is a very natural and ubiquitous constraint. It applies to many objects under regular usage, like cloth, skin, paper, of course, and the organs that we observe in surgery in particular. So in my case, this is what I'll be interested in. So this is a very strong constraint. It's somehow like the equivalent of a local rigidity. And mathematically, it's translated by the fact that the first fundamental form, which is also called the structure tensor, is preserved between the templates and the shape that the unknown shape we're trying to recover for 3D reconstruction. And armed with this new constraint, we can ask again whether we can solve the problem. So still, now we have 9 unknowns, not 3, because the local structure around the 3D point becomes an unknown in the problem, and it has 6 parameters. And the new constraints for isometry we have introduced just actually provide 3 constraints, preservation of the structure tensor. So we're still short of 4 constraints. That's even worse than it was with the previous model. So we keep enrich this problem formulation with more constraints. Now, what we introduce is this ellipse here in the input image, which represents this affine correspondence I was discussing in the pipeline. Once we have this ellipse, actually, we can enforce the fact that the local structure on the 3D surface projects to this observed ellipse here. And this projection is here, given as our third equation in the system. And it's basically dependent on the first order derivative of the camera operator, which we can trivially compute because the camera is known. But the good news, once we have this, is we still have 9 unknowns, but now we also have 9 constraints if we add up all of them. So the system is consistent. It has 9 unknowns, 9 constraints, and we can really wonder whether it's solvable uniquely. So we analyze the nature of the constraints for that. So the first constraint, the reprojection at 0th order, is linear. The second one is quadratic because we're multiplying unknowns with each other. And the last one, if we write it explicitly for the perspective camera, is quadratic as well. So A, this system is a quadratic algebraic system. Everything is polynomial here. So if we compute the theoretical bound on the number of solutions, it's quite high actually. 128, so it's too high for these general solutions to be interesting. However, the good news is that there is a single solution for the 3D point coordinates and only 2 solutions for the local differential structure around this point. Actually, if you're familiar with post-computation for 3 points, this system represents some sort of infinitesimal P3P system when we take the 3 points we're interested in very close to each other, infinitesimally close. So this is a good news, and also there is a very simple analytic solution to this system. So if one day you're interested in solving point reconstruction from a single point and the local first order differential structure that you can obtain from optical flow or local registration, there is a very simple solution to that for which you can find MATLAB code on my webpage, for instance. And so this is really good news. So in practice, for one point and the local differential correspondence, we can find a 3D point, so the depth, and we find two possible normals of the surface around this point. So this correspondence is the first order differential correspondence. It's affine correspondence, and we can compute it very simply with at least three different ways. One is to detect and match affine covariant key points. The other possibility is to compute optic flow and just keep the optic flow around this correspondence. And the third possibility is to use an image warp function that we fit to key point correspondences. So I'm showing how it goes for this warp function. Here, this is a thin plate spline that we have fitted between the template and the image, and we represent by this red grid. So if we fit this thin plate spline, we have access to the this affine correspondences very easily. So that's an example of reconstruction results obtained with this method. You can see the input image, and the grid you can see on the input image, which is superimposed, was obtained by fitting a thin plate spline. So this works automatically from SIFT correspondences. And on the right, you can see the 3D reconstruction we obtain. So here you can see another example, which is reconstructing a balloon. The template is shown on the top and the input image on the right, and the reconstruction on the left. So remember, this is a process that goes independently for each image. So there is no notion of failing because each image is processed completely independently. And this framework, SFT, has been extended in a number of ways, of course, to 3D templates. We have used it as well to calibrate the camera online, so we are able to compute the focal length. We're able to handle more advanced deformations than isometry. So conformal deformation, which preserve not length but angles. This is a weaker assumption. Equiareal deformations, which preserve local areas, so it's even weaker. We're able to handle affine cameras and also 1D structures. So you can see an example here. We have reconstructed the shape of the road sign just from a very simple template, knowing that the points were equally spread on the floor, and we were able to reconstruct the shape of the road just from this knowledge by defining a trivial template. So you can see the reconstruction of this white line on the right of the screen, and this is quite accurate. So I'll skip this part and discuss now the case of non-rigid structural motion, which is, remember, this case where we don't have a template. Of course, it's a more complex case because we have a much weaker knowledge on the structure of the scene that we want to reconstruct, and it's a real question on about whether we can actually do local reconstruction in this case. And I'll give a very brief derivation of what we have just to give you a feeling of how we can obtain and what's the main result. So this is joint work with Shefali Parashar during her PhD thesis in my group. So we started from this very simple modeling. We have two images. I'm not going to consider more for this simple derivation. We know the camera operator for these two images. Everything is done in camera coordinates, so we assume that we have local camera for each different frames, and we're interested in recovering the 3D structure, which again is different for each image because the object deforms across the images. So this is our model, and we start, as in the case of shape from template, by a simple point correspondence between the two images, and we start modeling. So for these 2 points, we have a non-3D points on the 3D surface, and we want to find their coordinates given the correspondence and the projection operator capital pi, as in the structural motion case. So we introduce two constraints, which are, of course, that the 3D points must project at the right location in the two images. So we have these two constraints. And we can start counting the number of unknowns and number of constraints to see if we can decently think about solving this. So of course we have two 3D points as unknowns. So we have six unknowns in total, 2 times x, y, z, and we have only 4 constraints because one reprojection is only 2 constraints in a single image. So of course the overall system is under constraints, and we cannot solve it uniquely. So we keep on modeling, and we introduce the local differential structure around the points. The aim of introducing this, of course, is to be able to model something on the deformation of the objects with isometry. And we introduce the local area in the first image to be able to reason about this local structure. So the further constraints we have are the third one here in the system, which is isometry, which just says, as in SFT, that there is no local extension around the point, and that if we project this local structure around the point, it projects to the image in the canonical observed structure into this image. So if we count the number of unknowns, we have 18, and we have 11 constraints in total. So we're short of 7 constraints, so obviously we still can't solve. So we keep modeling and adding constraints. We introduce the local differential structure in the second image, is AQ2 around the second point, and we introduce the constraint that the corresponding 3D local differential structure projects to this one in the image. So now we can count 18 unknowns, 15 constraints, so we can still not solve. And actually, we're a bit doomed here, because we have published a couple of years ago a theorem that says that if we keep trying to analyze things here with only first order, so differential first order constraints, no matter the amount of images that we can add to the system, no matter the amount of points we can add, we cannot solve locally for the 3D structure. There will always be more unknowns than constraints. So the way to go is to add orders, actually, to differentiate the surface more than that. And so it means like looking a bit further around the point on the surface. So the main result, like I was saying, is that at 0th order and 1st order, this is always under constraints, no matter how we put things. But a strong result we obtained is if we go to 2nd order, then it starts to be well constraints, and we can start solving locally. And we have shown that the 2nd order system, A2, can be reduced with some manipulations to 2 cubics in 2 variables that we could solve quite easily and quite stably. So this is quite a strong result, because it means that we can solve for 3D reconstruction very locally. So I'm going to skip the details and show you results of how it works. Here you can see this hand, a video of this hand bending, and on the right hand side, the point cloud that we obtained for this hand, superimposed with ground truth in blue for the last frame. So we obtained this ground truth just for the last frame, because we had to use another sensor for it. You can see the video again. And another results just for 5 frames here. So this was shot by another research group from CV Lab, and with the Kinect, so we had access for this data to some ground truth, and we could measure the error of non-rigid structural motion here, which was quite reasonable, being lower than a centimeter. So we have done extensions to this. We also proved that we could compute the focal length of the camera that we could handle weaker deformation models than isometry, so conformity and equireality, as in the shape from template case. But we also shown that with the affine camera, we couldn't locally reconstruct anything. So that's the takeaway message for both SFT, so the case with the template, and then NRSFM, the case without the template. If we make the assumption that the surface deforms isometrically, then in the case of SFT, we can solve from just one correspondence if we have the local affine structure at first order, which is quite simple to obtain from the image data. In the case of NRSFM, we have proved that we cannot solve at first order, no matter the number of images we use. However, we can solve as soon as we go to second order from at least 3 images with very mild ambiguities, actually. In general, we just obtain 3 valid solutions that we can very simply discard 2 of these solutions and keep the correct one. And from these, we can actually embed these solutions to robust and automatic optimization engine that can provide NRSFM solutions from input images. So the next point I want to discuss is actually an attempt we've made recently. This is joint work with colleagues from the University of Alcalá, and we have tried to solve SFT from a deep learning approach. So the pipeline is this one. We have as inputs an image, and we train a network, here this main block, to be able to infer the depth of this object, but also the registration of the object to a given geometric model of the object. And we tried it with a very naive approach, and it didn't work really well. So we had to add some refinement blocks. One is the depth refinement block, and the second one is the registration refinement block, and train the whole thing. And to add as well a post-processing to be able to obtain the whole shape of the object and recover the hidden parts, not just the depth of the visible part, but also the hidden parts. And for that, we used a handcrafted approach with an as rigid as possible deformation of the model, constrained by the output depth from the network. So technically, we have a fixed image output. We have blocks based on the ResNet 50. And what's important is that this is trained for a specific object, right? So this works just for one object and not is not object agnostic. So we have to train as many times as the number of objects we want to be able to process. However, a strong point that we improved on compared to previous work is that we can adapt to new camera intrinsics. So we don't have to train from images which were captured with the same intrinsics as for the camera, which is used at runtime. So this opens the scope of this quite widely, actually. We trained from synthetic data, which we could generate because, remember, this is shaped from template. So we have the template, which is an object model, which we load it with Blender, and with random backgrounds, we could generate a lot of data. Of course, the domain is different from the actual domain on the real images. So we had to use real images that we actually filmed with a Kinect, so we have access to the ground truth for the labels on the depth. Of course, we don't have access to labels on the registration because we have no means of tracking the position of each point on the object with respect to the template. And this is the way we trained our system with this data. So the last block, this as rigid as possible, is a physics-based approach, so it's not trainable. Then we had a first training step for the overall thing, which we trained in a supervised manner with classical loss functions, just from our synthetic data set. This is quite trivial. Then we fine-tuned the refinement block for the depth, and for this, remember, we had this Kinect data with ground truth on the depth, so we could do supervised refinements with these real data. This improves actually the performance quite a lot. And also we found that using a prior, a TV total variation L1 prior on the depth improved also the performance quite substantially. Then we had the refinements as our third training step of the registration block, which was self-supervised because we don't have access to real labels on all of the registration. So what we did was to minimize the photometric error between the input image and textured model, textured templates, by warping the former onto the later and measuring the color discrepancy. So these are some of the results we obtained. On the left, you have the input image. It works from just one image independently, of course. In the second column, you have the RGBD ground truth for this image, and in the third column, you have the results from our network in terms of the depth map with the error quantized. So as you can see, it's beneath 1 centimeter, even for quite complex objects like the dinosaur toy and the shoe. And on the right, you have the final output of our system, which is this as rigid as possible completion of the shape. So again, in the right column, we have access to the hidden parts of the object. So this is the strength of shape from template compared to things like monodepth, where you just have access to the visible part of the object and not to the hidden parts. So accessing the hidden parts of the object is extremely important in applications like computer-aided surgery, as you will see in the application that I'll show at the end of the presentation. More results on this deep SFT work. Here you can see that even though we have trained our network with images from Kinect, we could apply the network with very good results from data from other cameras. So in the middle column, you can see a comparison to ground truth for another RGBD sensor, which has completely different intrinsic parameters compared to Kinect. And even worse on the right for the GoPro camera. More results, so it's quite resistant to changes in occlusions, illumination, and drastic changes in pose, deformation, as you can see on the right, changes in lighting as well. Here I have a short video, so it works in real time with frame rates, if I remember correctly, quite close to 15 to 20 hertz. So you can see the results is very resistant to occlusions. It produces a segmentation map of the objects at the same time as the reconstruction. It is on par with a physics-based system as the one that I've presented at the beginning with this juice bottle example. So last part in the presentation is the application we're developing in my group on the application of all these techniques to computer-aided surgery. And I'm going to speak specifically of the case of laparoscopy. So this is the case we started with. Nowadays, we also do other types of surgery, but this is, I think, the most simplest one to understand, because in laparoscopy, most people are familiar with endoscopy, and this is actually endoscopy in the abdominal cavity. So basically, they have this this optics fiber with a camera, which is outside the patient body, and they make a small hole in the abdominal wall. So this is called a keyhole. And they introduce this camera and inflate the abdominal cavity with CO2 gas. So they create this working space. You can see an example of a patient on the right. And so they make several holes between 3 and 5 typically, where they introduce the camera. And the camera is here, by the way, and here you have a tool and another tool here. So typically there is an assistant who handles the camera, and the surgeon handles tools with their two hands, and there is an external screen, at least one screen. Typically, there are 2 or 3 screens, and the whole staff in the operating theater can look at the inside of the patient together. So typically, before the surgery, there is imagery, CT scan or MR scan of the patient to make the diagnosis, and the surgeon has access to this data. Either they remember it from before surgery, or they have access to it on a separate screen in the operating theater. Typically in this data, you can see what's going on inside the organ. So on the left, you have a slice of a CT scan of a liver. So that's the liver here, contoured in red. In this liver, there are two tumors, one in red here and one in green. And these tumors are endophytic. It means they're inside, really inside the organ. So that makes it a difficult case for the surgeon, because when they have to remove these tumors, if you look at the right of the screen, this is what they see actually. This is the liver, same patient, and they have to remove these 2 small tumors, but they don't actually know where they are, and they cannot touch with their bare hands. In open surgery, they would touch and find the tumors because they're more stiff usually than the rest of the tissue. But in this case, they can't touch. So they can't really accurately find them. They have access to ultrasound, but this is full of artifacts. This is operator dependent, and the learning curve is very flat. So this is really a difficult case, especially on this particular patient I'm showing. So what we have proposed and worked on for the past decades is to actually bring this CT scan information directly into the endoscopy screen during surgery, using a software that we have developed, which is called Hepatog. It means hepatic augmented reality in short, and that combines this preoperative CT and the intraoperative images. So this is, loosely speaking, the equation that we have to solve. The CT merge with the intraoperative image together to make a new intraoperative images augmented with internal structures like these 2 tumors in yellow here on the left, and the vascular structures, which of course the surgeon has to spare during incision. So what we do to start with is a 3D reconstruction of the patient organ. This is quite straightforward. We segment the CT. Remember, the CT scan is a 3D volume, right? We have access to voxels. So if we segment and do some marching cube, we have access to a 3D model of the external part of the organ and the internal parts with the tumors, etc. Then our problem is to register the 3D model to the intraoperative images, and it looks exactly like this shape from template problem I have theoretically discussed in the past slides. The difference is we don't have texture in this case, because the CT is not textured, of course, so we only discover the organ texture at surgery time. Nonetheless, we have access to some correspondences because there are some anatomical places that we can understand from the CT and the intraoperative images. So we still have access to correspondences, and from these correspondences, we have to figure out the shape of the organ seen from the of course the intraoperative configuration, because the organ deforms, as you can imagine, between the time where the scan is taken and the surgery, because the disease evolves, because the intra-abdominal pressure is changed, because the patient has moved, because the surgery tools will push on the organs, and etc. So there are many reasons for the organ to deform, but believe me, it actually deforms quite a lot. And this is the registration process in action. Here you have this blue mesh, which represents the mesh from the preoperative data from the CT scan, which is fitted to the intraoperative image iteratively. And once it's fitted, we are able to apply this deformation field that we compute from the visible parts to the invisible parts, which are the ones we're really interested in, which are the tumors and the vessel tree. So now you can understand why it's so important in our application to not just recover the depth of the organ, but also the correspondence of what we see to this prior model, to this template, because this is from this correspondence that we will be able to transfer the parts that we don't see, which are either the hidden parts of the dinosaur tool I have shown, but in this application, that will be the parts which are inside the object, the tumors. So in this surgery, you can see this is our surgeon here, our hepatic surgeon in the surgery theater. And you can see the laparoscopy screens here, the ultrasound console, and our prototype here. So this was used on a real patient, and as you can see, the surgeon started to incise here the organ to find the tumors, and we could measure post-operatively that the pieces of liver that were removed were, thanks to our guidance, really accurate. In this case, you must know that ultrasound didn't work to guide the surgeon because there were too many artifacts. So the surgeon was left blind, and without augmented reality, he would have had to remove a much larger part of the liver to make sure that all the cancer part was removed, because these were two cancer tumors. And I'll leave you on this other video. So this is yet another application. So still laparoscopy, but this time on a uterus. And we here augment two tumors in yellow and the uterine cavity in black here with the tubes, which are so the parts that lead from the cavity to the fallopian tubes, which are very important to spare, of course, for these type of patients towards future pregnancy. So that ends my talk, and I'll be extremely happy to address questions, of course.
Thank you very much, Adrien. This is so impressive, this video and the talk, all of it, from taking us from fundamental structure from motion and up to the deep learning era and showing us this transition. This is very interesting and exciting. Thank you very much.
Thank you very much.
We have a small delay with the YouTube streaming, so we'll give maybe a chance for people to ask their questions on the chat, so please don't hesitate. In the meantime, I have a co-organizer who has joined, Anis Qasim. I also missed to introduce Mohammed Adel, our moderator today. So guys, feel free to ask questions. We have also Ksenia Cherenkova, who is the co-chair of SHARP. She's also online, I see. And we have Gerard, who joined already, Ponsmol, who joined already. Maybe I can start with a first question regarding this deep learning approach. As you said, it's trained for one known template, right? So for one object only. I was wondering if this condition can be relaxed, and if you have a template of a category of objects instead of one fixed object, if it would work or if there are adaptations to do.
Yep, sure. That's a very good question, because being specific to just one object is, of course, a strong limitation in practice. So in order to generalize to a network able to cope with several objects at the same time, you have to consider two things. One thing is to be able to be generic to the shape of the object, so the geometry somehow, and the other one is to be able to be generic with respect to the appearance of the object, so the texture map. So we worked on the second aspect, and we have tried and managed to extend the system to handle objects of the same shape, but of different appearance. This is very recent work. We've just published it. So the paper is online, but I didn't have time to include the new results in the presentation. But this works almost as well as what I've presented for a single object. And basically what we did was to add a layer to the whole system that actually segments the object from the image, and the original contribution was to make an object segmenter that takes the input image, but also takes the texture map of the objects to segment as inputs, and is able to segment any object virtually given their texture map.
Mm-hmm. Now, this is also very relevant for the Sharp workshop, because you probably saw the different data sets that we have. We have the same category, which is the body shape, but there's also variation. There's, of course, different proportions of a human body, and then you have different sizes, you have women, men, etc. So there is a variation there. It would be interesting to know which level of variation you're robust to in shape, but also in texture. In our Sharp, we'll see that later during the workshop in Sharp. So we have also variations in shape and appearance, and also in texture. So we have naked or tight-fitting clothing. So mostly people are in sport clothing. So we have the same, very similar to the texture, the skin texture. And then we have large variation in clothing.
Mm-hmm.
And of course, there are models for human bodies, simple. I think that Gérard will talk about that, etc. So how can this be adapted to these existing models, and to which extent do we have robustness with respect to variation in shape and variation in appearance?
That's a very good question as well, and we haven't tried to, I mean, on humans yet, but I think we should at some point, and I think definitely there's an overlap between human-centered methods, human-specific methods, and the methods we developed, which are also applied to human eventually, but not on people, on photo of people, but on photo of internal organs. And then that's quite a different setting, though I think most of the blocks can be reused and taken inspiration from in developing these methods. So far, we're quite robust to variations in geometry, and we're actually working on what we've called weak prior NRSFM, where we're able to use a very generic prior. So you can imagine that rather than having the exact shape of the organ or of the object of interest, we have a generic shape. Like for this organ here, we could have a shape which would be just a sphere. And so that provides a very weak knowledge, mostly actually the topology of the object. And our goal is to use this very weak prior to improve non-rigid structural motion. And we have started to work very actively on that. And our first results are very encouraging.
That's very exciting, and I look forward to see more of those results. I see here a couple of questions on the chat, so I'll read them out loud here. So you have from Devesh, hi Adrien, very interesting research and application indeed. Could you say a few words about your recent IGCV work on the isowarp? Its context within your talk, an analogy with rigid multiple view geometry.
Sure.
This is a fan.
I'm moving back actually because this is something I have skipped, but which was in the presentation. So just give me a second. Oops. I'm just moving to the right place where this. Yes. It seems screen sharing stopped, right? So I have to share again. Can you see my screen?
Yes, we can.
Yeah, okay, excellent. So This is indeed the slide I skipped, and I think it's a very fundamental question. The question, if I understand correctly, I think I do because it was really clear, is if we're given two images of a surface that deforms isometrically, do we have geometry constraints on the optical flow, on how the first image deforms to the second one? And the answer is yes, and that's actually the contribution we have published in this IGCV paper that the question is referring to. So we have found that this function here, which is written eta, that maps pixels from the template to the input image, is actually not any arbitrary function. This function is constrained by a second order differential constraint, which must be fulfilled in order for this function, this warp function, to be a valid representation of the underlying world 3D structure projected to images. In perhaps simpler terms, you can imagine that when you take two photos of a rigid object, these two photos are related by the fundamental matrix. If they are not related by a fundamental matrix, it means they are not valid observations of a 3D structure. Period. That's geometry. So you can see this constraint we have formulated on the warp as an extension of this theory to the case of an object, of a surface, which deforms isometrically. And we have shown that the constraint, of course, is much more complex than the fundamental matrix, but in the end, obeys a second order PDE constraints, which is not that complex. Importantly, this is valid when you have a template. In the case where you would just have two photos of an object without a template, we have started to study this new case. It's more involved. We don't have the answer yet. We don't know if there will be a simple constraint to exploit. My guess is that there will be one, but we'll need at least 3 images to formulate it. But algebraically, it's a more complex case, and we're looking into it.
Thank you, Adrien. There's one more general question also here in the chat, and then we'll take maybe one more here and then move to the next one. So you mentioned 2 approaches, the handcrafted and deep learning. What could be a third approach?
That's a good question. I suppose that there's a third one which we haven't invented yet. By we, I mean the whole scientific community, of course. But I suppose these days something extremely worthwhile is to combine learning and physics-based models. Of course, is proven in numerous problems to be extremely effective. And as far as I can tell, in our approaches, in this deep SFT approach, we have a physics-based block at the very end, which is extremely fast and effective, simply because this is a subpart of the problem where we have physics-based constraints. They are simple to solve. There are efficient algorithms for that, and somehow there's no need for training. So why training a machine to approximate a complex function in the cases where we can solve it simply with an algorithm? So I suppose this is the answer.
This maybe leads to my last question, at least, is about the acceptance by the medical community and surgeons to use data-driven approaches, deep learning approaches in their surgeries. Well, you said if you have a good fundamental model, you probably don't need that. I'll let you answer.
Well, we actually do need some deep learning in the pipeline. So in the results I've shown, there's no deep learning so far, but our next step is, I mean, we have developed an improved method that embeds some deep learning, and that actually improves some parts of the pipeline. And again, that's a combination of deep learning and non-deep learning bits. But on the acceptance of AI in general and deep learning in particular by the surgeons, there is absolutely no problem. They're very enthusiastic with this. I suppose it comes from, of course, the hype of it because they can read about it, they can see about it in the medias, but also because they really believe it will improve healthcare. It will make their lives easier in several parts. So, for instance, in the systems we develop, we have to prepare this preoperative model by segmenting CT or MR. So at the moment, we do it by hand, and we take help from a radiologist or one of the surgeons. And it's a bit of a painful process. It's not very interesting. It's time consuming, and that's typically something that created a lot in deep learning. So that's the type of things they see when I say making their lives simpler.
Thank you. Thank you very much, Adrien. Maybe with that, we conclude your talk. Thank you so much. Very
Thank you for the
fascinating work and
invitation.
application. Stick
Thank
with us
you.
if you have some time. We'll have now Gérard Francois give a talk. So if you have a time, stick with us. Thank you, Adrien. Merci.
Thanks. Bye bye.
Bye bye.
Yeah,
Hi,
thanks.
Gérard.
Hello.
Thank you for your patience. But I'm sure you found the work very fascinating as well.
Yes, I did. It's really frustrating when you're still finishing slides and you hear an interesting talk on the background.
I hear that. I'll give you one more minute or maybe 10 seconds. I'll do your introduction. How about that? Let me introduce Gérard.
Before we start, actually, I should have checked this before, but the sharing, open system preferences, I don't see the icon for sharing activated. So
you are the presenter, so you should be able to share somewhere in there.
I cannot.
You don't see a share button? Should be.
I see the share button, but it's basically, it says allow WebEx events to record your computer screen so that you can share content. And so basically, I'm not sure. Let me go to preferences, maybe. Maybe you can introduce and then I can.
Yeah. No, I'm able to share. I don't know. Mohammed, you changed the setting? No? Yeah, I see you have the presenter sign, so you should.
I think I have to quit and reopen because it's a privacy setting, which I just changed. I'll quit and reopen, okay?
Okay. In the meantime, I'll do a quick introduction then.
Yes, go ahead.
All right. So you guys saw Gérard Francois, Professor Gérard Francois. I think he's not to be introduced. He's very known. So he's professor from University of Tübingen, recently joined the university at the Department of Computer Science. He's also the head of the Real Virtual Humans research group, senior researcher at Max Planck in Saarbrücken, where he was a faculty until recently. So his research lies at the intersection of computer vision, computer graphics, and machine learning, with special focus on analyzing people in videos and creating virtual humans, looking at real ones. That's what he says. So yeah, we'll wait a bit. I think everyone also is familiar with the very recent works of Gérard on neural implicits, implicit representations. Here we have Gérard. And also very important to mention that Gérard was a co-winner of Sharp last year, of the Sharp Challenge. And with his student, they're also finalists today. And that would be later on in the second session. Hi again, Gérard. Here we go. We cannot hear, but we can see the slides. If you do a full screen, like sharing. So
You have been muted by the host.
No, I'm muted.
You're unmuted now. Now we hear you.
Just around.
Yeah, it's when just joining, this happens automatically. So now we hear you, and we are ready to hear about your talk. So neural implicits, learning with neural distance fields, NERF, and all. The floor is yours.
One question, can you see the presenter mode or you can see the slides?
It is presenter mode, yes.
Okay, so that's not good. Okay, I'm not so familiar with WebEx. So stop sharing. Now share. I'll share the screen because I shared PowerPoint, so I'll share the screen. So now, what can you see now?
Still presenter mode.
Oh, I see. So what should I do to see the presenter mode and that you see the...
Is it this use slideshow there? No, that button. Not sure.
Share my screen, share application, maybe share
Presentation and tools.
PowerPoint. What can you see now?
Still presenter.
Okay, so maybe I'll just quit the presenter mode and see what happens. Do you know what I should do to see presenter mode?
It should be...
This is about moment. Make I try to just present your PowerPoint.
You have the mic, right? Go ahead.
Try just to present with normal without presenter view and see what can.
Yeah, I mean, yes, this I can do. I like to see also because I have comments usually, but it doesn't matter. Like it doesn't matter. Can you see now the screen?
Yes. Now it's perfect.
Okay, so we'll just do it like this. Yeah, thank you very much. I'm very excited to be in this workshop. And yeah, so basically today I'm not going to talk so much about humans like in many other talks from my group. Yeah, I want to basically explain a little bit some of the work we've done in neural implicits and also learning with distance fields. And I basically want to share this excitement that we have by this explosion of neural implicits and also nerve-based methods, which offer new possibilities for 3D shape representation and reconstruction. Yeah, so basically, at the most basic level, one of the fundamental goals of computer vision is to perceive the 3D world from pixels. And maybe the most difficult problem is like given a single image, reconstruct the 3D scene, the objects in the scene. And we're typically interested in recovering like a surface that can be rendered and that is complete, has no noise, and it's also smooth like real objects in the world. Sometimes we have not images, but we have other sorts of inputs, like for example, sparse voxels or dense voxels, or sometimes we are given like partial point clouds. And those inputs come from different modalities of sensors, for example, depth sensors or 3D scanners. For example, sparse point clouds can come from structure from motion algorithms, so they can be some sort of intermediate representation of computer vision algorithms. And typically we want to, at the end, we are interested in having a smooth, complete surface without holes or noise and without these voxel artifacts of voxels. So we're typically interested in these full 3D shapes that can be rendered. So it's clear that machine learning, and in particular deep learning, has there's great potential in machine learning methods because they are able to reason about multiple shape collections. They are able to reason about global properties of the shape as well as local properties. And so that's why there's been an explosion of methods trying to use deep learning for shape representation and shape reconstruction. When we look at the types of representations that people have used, we see people have used voxels, which are convenient for deep learning because the output can be well piped into these deep learning frameworks. However, these typically have and suffer from block artifacts, and also they are quite memory intensive, because if you have a cube, so basically things scale cubically with resolution. Points, on the other hand, are much more memory efficient, and so in that sense they are very effective. But however, like, it's difficult to render them. As you can see here, it's difficult to render a realistic bench from just points. Now, then we have meshes, which again, they can be rendered, but they are limited by the resolution. This means the number of vertices you use. And it's difficult to represent many different topologies with meshes, because it's typically the methods, what they do is they take a sphere mesh and they deform it to explain different objects in the world. And of course, this is not changing the topology. And this means that then it's difficult to represent different topologies with the same model. Meshes are very effective for representing objects that are well known, like humans, for example. But for representing a wider class of objects, they are not very suitable. And recently we have lots of deep learning methods that use implicit functions. And the basic idea is to train a neural network that decides for every point in space whether this point is inside or is outside of the surface. And then the surface is determined as the boundary. Implicit functions for shape representation is nothing new. We've known this for many years in computer graphics since basically the 80s. But what is new is the combination with deep learning, and this has opened a lot of possibilities. So I'm pretty sure that most of you already know what is an implicit function and how to represent a shape with an implicit function, but I just want to give like the basic idea again. So imagine you have this surface, which is this blue boundary here. If I want to represent this shape with an implicit function, I can basically define this function f of p that for every point in 3D space determines whether the point is inside, marked here with a red square, or outside, marked here with a blue dot. And basically, if I want to recover the surface, I need to find the boundary, the transition between the inside and the outside. In this case, if I have a 0,1 occupancy, I could say, okay, every point that takes a value 0.5, it means that it's the surface because it's at the boundary. Now, why is this representation useful? The main usefulness of this is that if now the surface splits into two, the topology changes. And the interesting thing is that we can differentiate through this change with no problem. We only need to take the spatial gradients of f, and there's no problem. If we had a mesh-based representation, it would have been very difficult because we would have to track which vertices are connected to which other vertices, and tracking all these changes and making the whole process differentiable is really, really difficult. All right, so how do we integrate this with this is well known. How do we integrate this with a neural network? And here's where these three papers came at CVPR 19, almost with the same idea, which is an obvious idea once you know it. But I think this is a property of good ideas. They are obvious once you know them, but they are not obvious, but they are not easy to come up with. And so the basic idea is that you train a neural network to classify every point as being inside or being outside of the surface. Typically, you're not interested in memorizing a single shape with a neural network, so you basically also have to condition on the input. And the input might be an image, or it might be a sparse point cloud, or an incomplete scan, like one of the scans from the Sharp workshop. And basically, you encode this input X into a latent code Z, and then you have a decoder that, based on this Z latent vector and the point, it decides whether the point is inside or outside. And then you can query many points, and basically at the end you can run marching cubes to recover the surface. And so the beauty of this formulation is that you don't train a network to produce the full shape at once, but you train a network to decide for every point by point. And I think more than the implicit representation, the point by point idea is what had value here. All right, and this is really good because now you can represent many different objects. The representation is continuous because at test time you can query as many points as you want, and you can represent multiple topologies. So these are all good news. Here the bad news is that we tried this for articulated objects like humans. So here the task is to recover a continuous surface from this voxel representation. And we observed that it didn't recover, these methods didn't recover very well the limbs of the person. As you can see here, the limbs are missing. And also another problem is that the output representation didn't retain many of the details that are even present in the input. So for this voxel representation of the input that you want to recover the surface from, you can see that the outputs are basically losing all the detail, and they are rather smooth. So okay, so we wanted to investigate what's the problem. Why can these models not reconstruct articulated structures? So the first thing to realize is that the input that we're sending to the network, X, in the case of sparse voxels or point clouds, it lives in a 3D space. And when we're encoding this input into a Z variable that is in an n-dimensional space, we're losing this connection. Basically, we have a loss of 3D structure because this latent variable does not live in a 3-dimensional space, but it lives in some n-dimensional space that has no connection with the original space. Therefore, it's difficult for the decoder to figure out the structure of the input. And the second problem is that we're sending point coordinates to the network. And this has no, like point coordinates have no information about the shape, because if I rotate the shape, the point coordinates will change, and then the decoder will have to memorize all these possible transformations that I can apply to a given shape. So there is no information in the points. So in that sense, this formulation didn't make a lot of sense because the networks are just memorizing which objects occupied which coordinates. And that doesn't seem to be learning and reasoning about 3D shape. So, okay, so in CVPR 20, in what we call IFNets, implicit feature networks, we presented solutions to those problems. And again, these are very simple ideas, but they are really, really effective. So given an input, what we do, instead of sending the point coordinates to the decoder, we are doing 3D convolutions on the input. And this is what I represent with this square. It does 3D convolutions on the input. And we obtain a multi-scale grid of deep features, from local information at the earlier layers to more global information at the deeper layers. The same as a CNN, but in 3D, with a voxel-based representation. So now the trick is, instead of, if I want to know the occupancy of a given point, instead of sending the point coordinates to the decoder, I'm going to extract deep features at the point location, at a continuous point location. And so for this given point, I'm going to extract deep features, and I'm going to extract these deep features at each of these layers, which will contain global and local shape information. And based on these deep features that encode the global and local shape information, I'm going to decode the occupancy of that point. So these simple changes actually lead to significant improvements. So let's look at mathematically what we're doing. So before we had models that take a latent variable z, which doesn't live in the 3D space, and point coordinates p, and produces an occupancy. And now what we do instead is to compute a multi-scale grid of deep features, f1 until fn, and we extract deep features at continuous locations in each of the volumes f1 until fn. And from this, we decode the occupancy 0, 1. So what are the advantages? Now we can reconstruct articulations. We can retain details and produce some details that are not visible in the input, like wrinkles, as you can see here. And the same model can be used to complete partial point clouds, as you can see here. So this is, the green dots are just the view of a depth image, and we can reconstruct the full shape from this depth image. So notice that in IFNets, we're not memorizing point coordinates, but the network is reasoning about these local and global features. And you can imagine that the encoder is learning many different shape statistics from more local to more global. So here's a comparison with, sorry. Here's a comparison with existing methods. So on the left, you have the input, which might be a voxel representation or a point cloud. And we want to recover the dense surface. So you can see that the previous implicit-based methods like Chen et al., Mecheder et al., they have problems reconstructing the articulated structures. And our model recovers the articulated structures and also produces much more detail, as you can see here. It not only works for humans, but it also works for other objects, like, for example, cars and any object in the ShapeNet dataset. As you can see here, we are recovering like more details than the other methods. Yes, and numerically, we compare to many of the other methods, and the conclusions are that the improvements are not minor, but they are significant. So it is really like we outperform other methods by a significant margin. And in 3D tasks, I would say that implicit feature networks are still really, really effective. And the code is online. I really recommend that you try it out for your problems, because in our experience, they work really, really well. And this is considering all metrics, so intersection over union, also chamfer L2 loss, normal consistency. In all these metrics, we outperform the previous methods. And it was a good timing, because the Sharp challenge came right when we just published the IFNets, and it seemed that it was ideal for this challenge, and we just adapted it to produce also texture. And so here's an input of the Sharp challenge, and you can see the scan has holes and a lot of missing data. And we were discussing with Julian, okay, like we should try, because it seems like very suited for the method. And actually, I thought without a body model, probably we're not going to be the best, right? I mean, using a body model will outperform us. But that's not what happened in the end. Like, it seems that the implicit feature networks were recovering a lot of the human structures without actually using a generative model, which was somehow like we were positively surprised by this. I think Julian will talk a little bit more about this later. This works also for different objects, as you can see here. These are also from the Sharp challenge from the previous year. And yeah, we were positively surprised that it can recover quite well the structure. So it really shows that it reasons not only about local structures, but also about global structures. And yeah, we were really happy to win the challenges last year, because this was also a confirmation that, that the implicit feature networks are quite effective. And yeah, Julian was also happy about the generous cash prize. So yeah, like it is a really generous, basically cash prize for the workshop. So thank you for the organizers for this. Okay, but there's problems. So one problem is that we're using an occupancy-based representation. This means that we're separated in we're considering only surfaces that are watertight. This means surfaces that separate the space into inside and outside. However, there's a lot of surfaces like open surfaces and manifolds or garments that do not satisfy this constraint. They are open and they don't separate the space into inside or outside. There is no such thing. Also, for example, a complex shape like a bus, it has inner structures. How are you going to define what is inside and what is outside? It's not clear. So we need to change the output representation. So implicit feature networks was focusing on the input representation, but here in a follow-up work, neural distance fields, we realized we had to change the output representation. And again, we wanted the simplest possible thing that would be effective. So what did we do? We actually changed the representation from an occupancy to an unsigned distance field. So people had used signed distance fields as a representation, but in the context of neural implicits, nobody had used an unsigned distance field. This was somewhat surprising, and the reason we wanted this representation is because in an unsigned distance field, you don't require the shapes to be watertight. You don't require the shapes to be separating the space into inside and outside. So this means that now we're going to train a neural network that predicts the unsigned distance. This means for every point P, we're going to output the distance to the closest point Q on the surface. Seems simple, but by just doing this change, we can represent a much wider, much broader class of shapes. Okay, so things are not as simple as they look, because now if we train a neural network to go from point clouds to an unsigned distance field, we can recover the surface as the zero level set, all those points that have zero distance, which is shown in white here. However, we cannot use marching cubes, because marching cubes require, again, a sign. It requires like to have a distinction between what is inside and what is outside. So we need something different. So the nice thing is that because this is a neural distance field, we can obtain the gradients very easily by backpropagating through the network. We can compute the gradient, the spatial gradient, right, with respect to the point. So with this, we can obtain this gradient field. And now we want to project points to the surface, because remember, we're interested in the surface ultimately. So, okay, we could follow the gradient until we reach the zero level set. That seems like one idea, but we can actually do better than this, because following like a property of distance fields, we can project a point to the zero level set with the following equation, which says, take P, subtract the distance times the gradient, and you will land on the surface. So why is that? If you look at the gradient, look at this equation here on the top. If you take the gradient, it's gonna point by just mathematically, it's just gonna point to the closest point Q. So that's clear, it's gonna point to the closest point. And now the question is, how far do I have to move to reach the closest point? Well, the distance itself, which is given by f of p. So that's why this equation allows you to project points in one shot to the surface. This was known in computer graphics, but is something that has been very little used in the literature. We found only a couple of papers doing this. Okay, so in practice, we have a neural approximation. So things don't work as nicely as in theory. So we had to project actually 4 or 5 times points from the outside to the zero level set until we could obtain an accurate reconstruction of the surface. Okay, so here we compare the results of neural distance fields with IFNets, which was the state of the art at that time. And you can see that neural distance fields for reconstructing shapes with inner structures, implicit feature networks, when they have to reconstruct shapes with inner structures, like cars, for example, that have chairs and the wheel and so on, it cannot, because it can only represent inside outside. In contrast, neural distance fields can recover all these inner structures. You can see here how the chairs of the inner side of the car are recovered and how all these inner structures can be reconstructed. Also, we tried it for open surfaces, like, for example, garments. So we trained on a data set of garments. We trained neural distance field to recover like the surface from a point cloud. And again, we could really nicely recover surfaces with holes. And yeah, basically this would not have been possible with any of the methods, but with neural distance fields, we can just recover these surfaces with any topology and any hole, any sort of, yes, they don't need to be watertight. So we can basically go further and we can use neural distance fields to recover, to reconstruct full 3D scene. So here, given a sparse point cloud, we are reconstructing a dense point cloud of a 3D scene I don't remember which data set this was. One of these, it was either ScanNet or Replica, or one of these data sets in 3D. So basically here you can see that, yes, this works quite nicely for a wide variety of structures. And yeah, again, it can reason about local and global shape properties. And notice that a scene like this, you would have never been able to define what is the inside and what is the outside of the scene. Okay, so because we have a neural distance field, we can also directly render it. The technique I showed before is to compute points on the surface, but we can also directly render the neural distance field. And for this, we can use what is called sphere marching. So you have this neural distance field and you go along the ray, and you can use properties of the distance field to go faster, to reach the zero level set faster. And so what you can see here on the top row is the input. On the second row, we're showing the depth, and we're also showing the normals on the third row, and also a shaded rendering of the depth. And we're also showing the back of the object here. This is just to illustrate that we do not need to compute points. We can directly render this field representation of the shape, or implicit representation of the shape. Okay, so we compared to the state of the art, and the most related work was a method called SALV from Jaron Lippmann's group, and they addressed one of the limitations of neural implicits, which was that they require watertight surfaces for training, but the output they produce is still a watertight surface, and therefore they cannot recover these inner structures of the car, in contrast to NDF that can recover these inner structures. And yes, again, like here, we're also significantly better. I mean, most of this improvement comes from the fact that we can recover inner structures, but also the results are also sometimes, even for watertight surfaces, more detailed than IFNets. So here, the comparison with IFNets on all ShapeNet is also significantly better. All right, so we started with a method that was for 3D shape reconstruction, but then we thought further and we realized this is more general. And we realized that we can use NDF to approximate a wider class of functions and manifolds. So we used it here to approximate linear, quadratic, and sinusoidal functions. And you might think, well, whatever, I'm not impressed by this because I can train a neural network and it can do the same. And that's true. However, if you have functions where you have multiple outputs for a single input, like this spiral here, take the x value 0. If you go along the y direction, you will have several solutions. First one at y equals 0 almost, and then, and then it will intersect at other points. This is what is called a multimodal regression problem. So you have multiple y outputs for a single input. And if you train a regressor, what's going to happen is that it's going to average across these multiple outputs. So this is a problem. But if you learn the density with neural distance fields, you can overcome this problem. So now imagine that you have the following regression problem. You want to predict y, and you want to train a function h that given x1 until xn, it predicts this y output variable. I can represent this regression problem with implicitly by learning an implicit function for which, for the values of the function, it will take 0 value. So for all the x1, xn, and y values, y in this case given by this h, will be at the 0 level set. Now, how do I do regression? I start with a given x value, and I can do ray marching until I intersect with the 0 level set. And here we're using the same technique of sphere marching to do regression. And the nice thing is that we can now represent complex manifolds using these neural distance fields. And I think the takeaway is that we start with a pure computer graphics technique to address a core machine learning problem, which is basically standard regression. So we're also excited to try this for more high-dimensional data and see like if we can use this also to approximate density functions and so on. All right, so let me give you what I think are advantages and disadvantages. It's not all good news. So when I compare implicit functions to parametric meshes, basically we win in terms of ability to produce different topologies and ability to produce details. It seems like it's also suitable for learning, but we're losing in control. So parametric meshes are still very lightweight. They are easy to parameterize. And if you want to deform and control implicit functions, you can still do it. And we're seeing works doing it, but it requires a little bit more of work and it's not as easy. All right, so it makes sense to consider like some sort of combination of these well-known parametric models and these neural implicits. And LoopRec is an instance of this. So in LoopRec, we're addressing a problem that is also very relevant to the SHARP challenge. The problem is, given a scan, I want to deform a human template to explain the scan. Okay, and this is not just spitting out the surface that you're interested in, it's deforming a known object to explain the scan. And the advantage is that then you will have control. For example, if you're deforming the simple model, you will be able to then change the shape and change the pose. This was presented at NeurIPS last year. And so let me explain what this is about. So in traditional registration, you have the following problem. You have to deform the model, which is this guy here in a T-pose, in order to explain the scan, which is this basically this surface you see here on the left. And typically you have to find correspondences from the scan to the model. And so this is step one. And these correspondences you can find using key point detectors, landmarks, closest points, using a supervised network that predicts correspondences, your favorite method. And then in step two, you have to minimize the distance between SIs, the scan points, and the model points MJ. Okay, so you have the following minimization problem over correspondences C and model parameters X. This might be the pose and the shape, the deformation modes, depending on the model you're having. And you're summing over all the scan points, and you have to minimize this distance. The scan point minus the model point MJ deformed to explain SI. So M big here might be the simple model or basically your favorite deformation model that you think will explain the sort of deformations of the data. Okay, so what are the problems? The problem is that this is instance specific, it's prone to local minima, and it's not end-to-end differentiable. So the question we were posing is, can we learn a correspondence predictor, f of phi here, that maps from scan points to model points directly using a corpora of scans? And even more, can we train this without supervision? Using the tools we know from model-based fitting, can we somehow integrate model-based fitting within the learning framework so that we learn the correspondence predictor? So the key idea is you have a function f of phi that maps from scan points to model points. These model points M will be deformed according to, in this case, the simple model, in order to explain the original scan. So here on the left, you can see the deformed simple model to explain the scan. And the scan has been colored according to this UV coloring of simple to illustrate that for every scan point, we know the exact correspondence to the model. All right, so this sounds easier than it really is. Because, first of all, how can we train the network f of phi and optimize X, the parameters of the simple model or your deformation model, without supervision? Another key question is, how do you ensure that the network predicts always correspondences to the model surface? We know that integrating hard constraints to a neural network is hard. So this is not obvious how to do. And third, how to integrate correspondence prediction within model fitting. So let's go step by step, and let's address point number 1 first. How can we jointly optimize over the model and the correspondences without supervision? Well, the trick is using this loop, and you can have a loss over network parameters phi and instance parameters mathcal x. This means all the poses and shapes and non-rigid deformations of all the scans in your data set. And then basically the loss is summing over all the scans from J1 until N and summing over the scan points, and is minimizing the distance between the scan point and the model points MK deformed to the scan, okay? And the trick here is that MK, which are the model points, are predicted as a function of the scan itself. So you have f phi of S that goes from scan to model point. Okay, that seems intuitive, but the question is, how do we guarantee that the network always predicts a point on the surface of the model? That's not easy to do. Well, I can use UV maps, and UV maps, you probably know about them, like it's a 2D unwarping of a 3D of a surface embedded in 3D. You're unwarping it into a 2D plane. And so basically for every 2D point here, you have a corresponding 3D point of the model. So you can train a network that goes from scan point to the UV map coordinate U, and then from the UV coordinate U, you can go to the model point M, which is in 3D. Okay, you could do that. However, the boundary of the UV map is not differentiable. UV maps have distortions, and also I'm not sure about you, but I don't like UV maps because you have to cut them. You have to design them manually, and they have like these annoying boundaries which are not differentiable, right? So it doesn't seem like a very elegant solution. So the question is, why don't we learn directly the mapping from the scan point to the model point M in 3D? Well, the main reason is because this prediction can lie off the manifold. And if you have a neural network that predicts off the manifold M is the surface here, what happens is that the deformation model, in this case simple, is not defined. So simple basically deforms points on the surface to like the post or shaped space and so on, right? If you are considering a point that is not in the surface, I mean, simple is not even defined. So basically, if you want to evaluate this and you're off manifold, you don't even know what to do. There's no derivatives, there's no function defined. So we have a problem because we cannot train. So how do we solve this problem? The key idea is that for every point, we're going to assign a simple function. And the simple function we're going to assign is the one from the closest point to the surface. However, we cannot, during training, we cannot find closest points to the surface because this is, again, not differentiable. So what we're going to do is diffuse the simple function from the surface to the full 3D space. And this diffusion is driven by the distance transform. So what we have now, and this is what is illustrated with this coloring, is that for every 3D point here, we know which simple function to apply. And with simple function, I mean, you can think of simple as a function over the surface. And now we're diffusing this function over the whole 3D space. Why are we doing this? Well, let's look at this. So simple was defined on model points on the surface, and it was giving us a way to deform these points. Now we have another function, which is not defined on the manifold, is defined on all the 3D space, R3, actually in this canonical space, which is basically not all R3, but only in this canonical space. And now this G knows what to do for points that are also off the manifold. And it's even better because now we have well-defined gradients of G outside of the surface, which means that we can train this self-supervised loop reg formulation. Okay, during learning, we have well-defined functions and derivatives of the manifold. That's good news. However, we don't want the network to keep predicting farther and farther away from the surface. Because remember, we're interested in predicting points on the manifold. So we need to add an additional constraint. And so this is basically a Lagrangian constraint that forces the prediction of the network to lie in the manifold. How do you force predictions to lie in a manifold? Well, we have the distance function, so it's very natural to consider the distance function. We want the predictions of the network to be on the zero level set, which is the surface. So we need to include this constraint over here. Okay, so with this, how does this change? We had before the simple model, which had to be evaluated at points that are off manifold. We had a problem, we couldn't train this. Now we're replacing by G, which is well-defined all over the space. So this is good news. And we need to add this Lagrangian constraint that is forcing the network to predict always on the surface of the simple model. And that's it. That's the idea of LoopRec. And you can train this. And the interesting bit is that this does not require supervised data in principle, theoretically. In practice, we needed a bit of warm start. So we need 1,000 scans to initialize the process, because otherwise it converges to local minima. But once you've done this warm start, you can add more and more scans. And this is what we're showing in this table. On the first row, we show the vertex to vertex error. And this, as we move along the columns, we're showing the amount of unsupervised data. This means additional scans that we are adding during training. From 0%, so 9.3 would be the error you get with the supervised warm start. And you can see that the error consistently decreases until we use 100% of the scans. In this case, we're 2,600 scans. The error decreases up to 1.5 centimeters. This is not surface to surface error. This is vertex to vertex. So it's a very demanding metric, and it's working quite nicely. The surface to surface distance, we also evaluate, and we go down to 4.2 millimeters. All right, so we also compare to the state of the art to, for example, 3D coded, which was a popular method for non-rigid 3D registration. And yeah, we perform significantly better. And yes, we also perform better than an optimization-based method. And that's because like these optimization-based methods, they work well when you have good initialization, but they don't work well when you don't have good initialization. So the code for the registration, a lot of people have been interested in this. It's online, and I also recommend that you check it out, because a lot of people have asked for this code. We didn't have it before, and now it's available, so you can check it out and let us know if you run into problems. Then we can see. Right? How are we doing on time?
Not that good, but we started late. We started late, but we are cheating a bit here, Joel, because we had the 30-minute break that I think we'll just use.
Okay, I see. Yeah, let me explain this very quickly, and then I go to the conclusions. Yeah, so this is basically the last thing I wanted to present is like the work we've done on generalizing NERF to multiple scenes. So not to make it scene specific, but to generalize it to multiple scenes. And the trick is similar to the trick we did to generalize, to make neural implicits work better. So in NERF, you get a point and a viewing direction, and you predict the color, the density. And probably most of you are already familiar with NERF. The problem of doing this is, again, you're memorizing mappings from point coordinates to colors and densities. So what we're interested here in what we call stereo radiance fields, and this relates a lot to the first talk from Adrian. We're integrating classical stereo within neural rendering. So our goal here is not to have NERF for one scene, but to have NERF for multiple scenes, all in the same model. So basically, prior work is memorizing, is training a neural network to memorize the scene, and then you can render the scene from multiple views. And what we want is from sparse set of views, as little as 10, we want to produce novel views of any scene, not just one scene, but any scene, right? So the difference is that NERF requires dense input, whereas we can work with sparse input. And we do not memorize a scene, but we are basically integrating classical stereo to reason about like the multiple views of the scene. And I'm not going to get into detail. I think Julian might go a little bit more in depth, but the basic idea is to use these photometric consistencies. So from classical stereo, we know that if a point is on the surface, when you project it to each of the views, you're going to have photoconsistent patches, right? Things are going to be photoconsistent. If you consider a point off the surface, things will not match visually. So our idea is, why can we not use this within the neural network? Why don't you send this information to the neural network to reason about what is surface and what is not surface? And yeah, very quickly, that's what we do. We project a point to each of the views, and then we have a neural network that processes like the like image-based deep features for each of the views. And basically, we learn an ensemble of case similarity functions that compare pairs of images. And from these, it can decide not only the color, but also the density. So you can imagine that you're having a neural network, which is kind of like NERF, but it's not mapping from points to color and density, but it's mapping from pairs of image features to this color and density. And by doing this trick, the network is not memorizing, but it's reasoning about the structure. So it's sort of doing a little bit of geometry within the network. And just very quickly, and with this I'll finish. So basically, this is some result. This is a result used. So let me explain what this is first. So the input to the model is only 10 images shown here on the left. This is in contrast to the hundreds of images that were required to train the NERF model. And what you see here is our model after being fine-tuned for a few minutes to these 10 images. And with the screen, you can also see our model. This is the result of NERF. And you can see that we can get much better reconstructions than NERF, although NERF has been trained for, I don't know if it was like a day on these 10 images. All right, because we're short on time, I'll just conclude. There's a lot of work, there's a lot of exciting work that is coming. And of course, I didn't have time to basically draw the connections with other works. And there's a lot of connections between what I presented and many other works. There's a very nice compilation of works by Vincent Zitzman and also Frank Delaert compiled a list. And yeah, it's amazing the amount of work that is coming. And I think there's a lot of opportunities to yeah, combine like these neural implicits with more classical methods to make progress. Also, in my group, we're very interested in human behavior. I didn't have time to talk about this, but if you're interested in this, please check out our recent paper, Human Positioning System, where we are able to, for the first time, like using only wearable sensors, capture the human motion and register it within a 3D scene. And we were very happy that this was selected as a candidate for best paper. And now we've released the code and data. And we're hoping that this will promote researchers to work on this space of humans and scenes and egocentric vision and so on. All right, and to conclude, I hope I convinced you that neural implicits can represent multiple topologies. They are continuous. They have a lot of good properties. I've shown several papers that basically the main message is that if you decode based on deep shape features instead of point coordinates, you will reason more about the shape and the structure. And I've shown neural unsigned distance fields, which allow to cover a much broader class of shapes. And I've shown a non-rigid registration method that can be learned self-supervised, again, using these distance fields to make this whole process differentiable. And last, I want to point out to the software. So we try to make all our code and data available, and we want to make it easy for people to use. So if you run into problems, please let us know, and we'll try to improve the code also so that people can build on our work. And thank you very much, and I'll be happy to answer questions.
Thank you very much, Gerard. This is very exhaustive and very timely. You went through different representations. This is very fitting to the workshop. In fact, you're kind of touching on the panel discussion we want to have later. Thank you very much. I'll turn around and see if in the room there are questions.
Yes, I have.
You have the mic, huh?
Yeah, this one. Thank you, Gerard, for this very nice presentation. I really like it. I enjoy it.
Thank you.
I have just a question, please, regarding these neural distance fields. I was impressed by the surface reconstruction on the scenes, on point clouds of scenes. Did you already test it on some kind of tasks related to edge-aware reconstruction, for example?
Edge-aware reconstruction?
Yeah.
Can you give me more details? What do you mean with edge-aware reconstruction?
That's challenge 3 of Sharp.
Okay, sorry.
Go ahead, Dennis.
Sorry.
So yeah, basically, like, imagine that you have a point cloud and you want to reconstruct the surface and you want to preserve, like, for example, the sharp features on this point cloud and be reconstructed. So this is what I'm meaning by saying edge-aware reconstruction.
I see. We're not doing anything in particular to preserve the edges. Yeah, I would have to think. I don't see why it shouldn't be able. I mean, okay. So, I mean, neural networks are smooth functions, so it's possible that these edges will be smoothed out, and maybe one would need to do something. I mean, definitely in geometry processing, people have done a lot of these things. Like, it's similar to anisotropic filtering, where you sort of when you're doing smoothing on an image, you're basically detecting where you have a transition and then you don't smooth. Maybe during training, you have to apply some sort of anisotropic filtering, but it's difficult because you don't know the output during testing. Yeah, I mean, actually, I would have to think more about this. I don't know. I don't have an answer for this. Sorry.
Okay, thank you. I have another question, please. It's related to the template deformation, because we have worked in the past on this kind of methods, specifically 3D coded network. So you said that it's usually not a good idea to impose hard constraints in neural networks, right? And this Lagrange.
Let me specify. So it is not. It's not that it's not a good idea. It's that it's not possible. Typically.
Okay.
Like, it's very difficult to impose a hard constraint. You can impose a soft constraint in the loss function, but imposing a hard constraint is really difficult because the network will always produce whatever, right? You cannot control it.
Okay, thanks. And another question related to this work again. How is robust to partial data? Because if you are doing some kind of 3D correspondence, at some point, like in real world applications, you will have to deal with this partial data when doing, yes.
So the question is, what's the loss?
How robust?
How robust is it?
How robust? Well, I think it's more, well, it's hard to quantify, but I mean, for the Sharp challenge, there's a lot of parts, like basically mixing data, and it worked nicely. So that was a surprise. Actually, sometimes I was very surprised to see the full arms recovered. This was surprising to me. Like, I was not
We were
expecting.
equally impressed.
Yeah, so the full arms I was not expecting, right? I mean, I was expecting
Yeah.
small holes and stuff like this, but the full arms, no, I was not expecting. So it is quite robust. The annoying thing is that you need to train. I mean, this is what the advantage of a generative model is that you can fit it to any kind of input. But the implicit feature networks or NDF or SRF, these methods are discriminative. You give an input and they spit out an output. And the problem is that you need to train them for every type of noise that you expect to have. So if now you have holes that are twice as big, maybe you have to fine tune on this kind of noise to make it work well. It can generalize, but probably if you want the best performance, you will have to fine tune on this. And this is where a generative model is more, it's more beautiful in that sense, more elegant, because you basically can fit it to any kind of noise, right? But these discriminative methods are surprisingly effective, I have to say.
I'll ask here a couple of questions from the chat. So you have here Yang, who says, hi, Gerard. Could you please comment on BARF, which optimizes camera poses while reconstructing 3D scene?
I didn't have time to read the paper. I heard about it, but I haven't read the paper, so I cannot comment.
Okay. And Brinda says, does it, talking about neural distance fields, does it address surface concavities?
Yes, basically, I mean, all sorts of surfaces will be can be reconstructed. It just depends on what you've seen during the data, but we're not doing anything in particular to address concavities or convexities of shapes or edges and so on. It might be that results look a little bit smoother than reality. That's possible. Yeah.
Mm-hmm, mm-hmm. I'll ask one question myself. First, congratulations on this loop reg. I mean, this is great, and it solves a lot of problems. I mean, 3D coded was also a very good approach. One of the biggest challenges is this registration, point-to-point correspondence. My question is also linked about to the 3D body tech data is how robust is it? How can it handle clothing and variation in clothing? Here, when you have the simple model, or tight clothing, I think it seems relative easier. But what happens when you have also changes in topology due to clothing, for instance?
Yeah, this is something that LoopRec does not address. With LoopRec, usually the scans we have are relatively tight clothing. And if you have like larger clothing, it will look as good as you can deform the simple model to explain this sort of clothing. And we have several papers that it is actually not bad. I think even like white clothing, you can represent by deforming the mesh, because then the mesh can deform quite a lot, right? But if you have a skirt, for example, yeah, you will have to deform legs to explain the skirt, which is not what you want. And so for these, this brings a whole new set of problems. So the first problem is like, what is the right correspondence? You want to register everything to one template of every garment category, or yeah. So first you have to define mathematically what you want, which is not so clear, right? With different clothing, what you want, because you cannot register.
Without having a template for your clothing. So keeping just the simple model, for instance, and considering that it's somehow a deformation of it. Is it something? Yeah.
It will look as good as it would look deforming the simple model to the scan, which we know the limitations this has. Now, I'm not sure, maybe the correspondence network, if it hasn't seen a lot of these scans, maybe it produces crappy results. This I don't know. We would have to check. Check.
One thing that I noticed from the tutorial on simple beginning of the week, I believe, from Michael, a comment was that registration indeed was one of the biggest challenges, and that So deep learning could give the first initialization, but then there's nothing that beats a classical optimization approach right after. Did you use that strategy in LoopReg?
Fully. If you look at the formulation, I mean, I agree 100% with Michael. If you look at the LoopReg, if you look, the formulation incorporates the optimization at the end, right? It's just. Let me go here from current slide. So if you look, like, this LoopReg goes from, with a neural network, you predict the correspondences, but then given these correspondences, you optimize the model parameters. And this step of optimizing this simple model to fit the scan, this is more classical, right? And this step is still there also at inference time. The only thing is that once you have good initialization of correspondences, then you can very nicely fit the model.
Absolutely. All right, thank you very much. Let me see if we have one extra question from maybe Ksenia. Ksenia, who is also co-chairing the workshop. We don't see her, so maybe not.
That's here. Can you hear?
You're here. Okay. Yeah. Hi, Ksenia.
Hello, everybody. Hello, Gerard. Thank you for a very nice and very relevant talk.
Thank you.
And my question is probably addressing the texture of the scans. So would it help to find correspondences if you use the textural cues as well? For instance, in the LoopReg, if you use the parameter table, which also
absolutely, I think it could help. For example, I mean, for the face, the texture tells you also where you are, right? For the clothing,
but at the same time, it gives more variability.
Yes.
All this clothing and
yeah. It depends. I mean, probably, like, the answer is it depends on how much data you have, and probably we don't have enough data to learn something useful. So I think you're more in danger to learning spurious correlations than to learning something useful. I mean, I could imagine this could be useful, for example, like hair are of a particular color, skin has a particular color, then shirts have some sort of texture that can tell you this is a shirt and it's not a pant. But other than that, yeah, texture would not be so useful, I think.
So you don't think there is a good way to try it in the LoopReg formulation?
If you're registering to a garment, then yes, because the texture will tell you the boundaries. And if you care about registering the boundaries accurately, then I think it can be quite important. But if you're just interested in deforming a single surface mesh, then I think texture will bring more problems than help.
Or maybe the opposite. It can give you some kind of masking of where not to fit, like.
Yeah, I mean, I fully agree. The problem is, like, we're talking about maybe thousands of scans, not millions. And these thousands of scans will have particular colors and skin colors. I think you're more in danger of overfitting. That would be my worry, I think.
All right. Yeah, thank you.
Yeah, that would be. I mean, it's a problem.
You are at the
and
sharp,
I'm eager to try the code you posted.
Yes. Please try and let us know. I think Bharat, the first author, is adapting it because this was implemented in some old library in PyTorch, and now he's adapting it. But yeah, the new version should be up soon. Yeah.
What's new now?
I wanted just to conclude to say that, at Sharp, the story started from texture with 3D shapes. So we're pushing also the texture and seeing how the texture can complement and actually help further. Hence the questions.
Yes. I think, I think it can help to, if you're interested in segmenting, for example, the body into clothing and skin. I think that's a very relevant problem for many applications. If you want to simulate clothing on top of the body, you need to separate it from the body. There, you need the texture, otherwise it's going to be very difficult to segment. But to know, maybe I'm wrong, maybe I'm just talking from intuition, and I'm just, many times it's been like this. You have an intuition and then you try experiments and it's a different thing.
I was about to conclude, but now I see a question. Maybe we take it as a last one. The question says, did you look into sinusoidal activations, also known as siren?
Yes. Actually, let me think. I think neural distance fields, or SRF, one of the two or both, have this high dimensional features at the network. I mean, so there's two things to this, because we're not mapping from point coordinates to the output. This was less of a problem for us, right? Because we're already extracting deep features to map to the output. So typically we do not use the point coordinates themselves. But when we do use the point coordinates, then yes, we definitely use these high dimension features like sinusoidal activations and Fourier features and so on. Yeah. For a
very
more
good
project, we
question.
also use them. Yes. So this, it is recommendable if the input to the network are point coordinates, definitely use these, because otherwise it would be too smooth.
Thank you very much. I think that was the last question. It was very, very interesting. We hope to see you a bit later at the panel, I hope.
Absolutely, yes. Thank you very much. Bye-bye.
Thank you, Gerard. Bye-bye. All right, everyone. So as I said, we're cheating a bit today. So we had like a 30-minute a break between the two sessions, but we won't manage if we take that break. So what I suggest is that we continue the workshop, especially that we have 5 finalist presentations that we want to fit to accommodate everyone. So we'll try. So I'll make my part very short. Let me see here, and it's basically just going. Doing an overview of the challenges, especially to introduce the finalists. That way we can look into the challenge 1, 2, and 3. Thanks again to our plenary speakers. I think that was really nice and very fitting the workshop. Now diving directly into Sharp. The goal, if you tuned in, you guys know that it's about reconstructing 3D meshes. The first part was a lot about using texture for that, and you'll see with challenge 3 we added that edge reconstruction in it. Right. So 3 challenges. First one, recovery of human body scans. Second one, recovery of generic object scans, and the new one this year, from an addition from last year, is a recovery of feature edges in 3D object scans. This was the timeline that participants who are connected hopefully know very well. We started in December. We announced the workshop, and it went. Let me see if there's a pointer. But yeah, guys cannot see pointers. So it went into the registration. We extended a bit. We extended also the submissions. So it was planned for 18th of May, and we pushed it until the 11th of June. Some of you managed to profit from that and improve their results, and we'll see the details of that a bit later. And today, we will announce the big winners. So again, I like to tell the story of Sharp. It really goes back to this 3D Body Tech data set that we first published in 3DV in 2018. It was mostly, this first version of the data set is tight clothing. So naked bodies. And so it's composed of 400 bodies, 200 subjects, 100 males, 100 females, with 2 poses per subject, variation in, well, about 300K vertices and 600K faces. And the main point and our selling point for this data set, I think, is very unique as compared to the other existing data sets, is the high resolution texture that comes with it. And then in Sharp, in the first edition of Sharp and ECCV of last year, we introduced the extension of 3D body tech with variation in clothing, different poses. So we had about 2,500 scans there and about 6 poses per subject. And the story really goes back to 2017 when we started collecting data here in Luxembourg at different places, sponsored by Artec, who are still sticking with us today as well. So we used the scanner, the Shopify scanner. So we called it Let's Get Shopified campaign. It went into from summer 2017 to 2018. And finally, we closed it with a big event at the biggest mall in the country in the summer of 2018. And I'm looking at Mohammed, who is very involved in there. So it's a long story, this Sharp and 3D body tech story. The second data set for Challenge 2 is the 3D Object Tech data set, which is part of the repository of Artec, ViewShape. So it is a subset of generic objects, also with high resolution texture. And for the challenge, we had about 2,000 textured 3D scans. One point before going to the next one is the variation that we had in this data set from the geometry and the resolution. And now the new addition, which is the CC3D dataset, which stands for CAD Construction in 3D dataset. This one was actually published first time in ICIP 2020 with Xenia leading this activity. So here for the workshop, for the challenge, we shared about 50,000 pairs of CAD models and their corresponding 3D scans that we virtually scanned. And again, here also the complexity of the challenge of the problem is the variation of the data. So you can see very simple objects like these ones, to complex ones. And here I'm not showing the pieces that come inside. And the pairs that we provided are basically the CAD. And Anis was asking earlier about the edges because he has been looking at length on those edges. So you can see here on the sample the very sharp edges. And when you go to the corresponding scan, they become very smooth. And this is the problem and the challenge that we offered, the additional one that we offered this year. So we gave these pairs of CAD data and their corresponding corrupted scans. And the goal was to recover the what we called filtered edges, basically the edges that we can see from outside. And we filtered them from the original edges that come with the CAD model, even inside. And yeah, the task was really to recover both edges, but also the shape corresponding to the original CAD object. That's challenge 3. In brief, so challenge 1, recovery of human body scans. Here you see some samples. You see the holes, the level of holes, and this is from last year. In fact, this year we had an additional level of complexity with even bigger holes. Similarly, for challenge 2, except that the objects in question are very generic. A lot of variation, as you can see in these two examples. And yes, today is the day we will know to whom this 9,000 euros will go. Of course, it will be split between the three challenges, and only Ksenia knows the answer. So Ksenia will give us that information after the presentations of the finalists. So I estimated roughly that it would be, yeah, in about an hour and a half or so. So with that, I would like to almost conclude by acknowledging and thanking all the co-organizers, Ksenia for co-chairing this year's workshop, Alexandre Saint, David Fofi, Gleb Gusev, Bjorn Ottersten, Anis, who is present, Anis Kassem, Konstantinos Papadopoulos, and of course, as I said, you know, the story goes back to 2017, 2018, etc. And this is an effort that came from kind of nowhere, with everyone chipping in with his and her time. And this is all the past members of my research group and the current members who are still here present today. So that's the CVI2 research group. So I really insist and would like to thank everyone, and especially Mohammed, who is our moderator today, and he's doing the streaming, etc. So thank you very much. Of course, without Artec, this would not be possible, our sponsor and industrial collaborator. And also would like to acknowledge the continuous support of the funding agency in Luxembourg, the Fonds National de la Recherche. With that, I think you understood that we skipped the break, but I managed to bring us kind of into schedule because we will fit 2 extra presentations of finalists. Those are recorded, so we'll run them. I don't know if the presenters will be joining online. I will check that and we'll communicate that on the chat. And in all cases, please leave your questions, and if they're not here, we'll communicate the questions to them. And then after the, and of course, we have live presentations. We have 3 finalists who will be presenting, 2 internal, and Julian, who won last year, would be presenting as well. So stay tuned. Afterwards, we'll give the winners and analyze the results. Anis will help us look into the details of all the proposed solutions. And finally, we'll have, I hope we manage to reach to the panel discussion on time, because we have some precious guests, basically the co-chairs, program co-chairs of 3DV21. So these are exceptional guests who will be coming, and they're experts in 3D. So they will be coming to talk to us about 3D representations of objects in general. And with that, we'll start maybe the first a recorded presentation. I suggest to go with the presentation of Yusong Lee, if you can run that for us, Mohammed. It's about 12 minutes or so.
Hello, my name is Yusong Lee in Nigeria, South Korea. First of all, it's a great honor for me to participate in the challenge with this workshop. Now, I'll present about my solution for the challenge 3, recovery of the feature matches in object scans, which is strongly based on SC3 transformers, 3D local translation preventing attention networks. different equivariances and y-unities. For each data, we generally use proportional networks. For sequential or purely data, we can use reinforced neural networks or LNPs. This style is based on inductive bias of data flow. For image classification, we expect that translation in XY direction does not change the result. For image segmentation of the test, we expect that translation in XY induces same translation in the result. Therefore, it's better to use architecture that preserves spatial translation. Similarly, for the time series data, we expect that translation in time makes no change in the resulting piece classification. Or in other texts, we expect that translation in time induces the same effect in the result. Therefore, it is better to use architectures that preserve temporal translation. These make the concept of group equivariance. A group of transformations, like translations, act on data domain. And we expect that layers in the networks conserve such transformations. In the other words, each layer defines group equivariant maps. In the case of a group of 2D translations, CNNs consist of group equivariant layers. In the case of group of time translation, RNNs consist of group equivariant layers. This happens in many cases. We sometimes unconsciously assume the existence of symmetry on data domain. This inductive bias dramatically reduces complexity of networks. When we assume 2D translation symmetry, CNNs are effective solution. When we assume 1D translation symmetry, background models are effective solution. When we assume permutation symmetry, then graph neural networks or transformers are effective solutions. Mathematically, when such transformations act on data vector space, we call such data space a group representation of the group of transformations. Then, group equivariance layers are mapped between group representations. Therefore, it rotation equivariant networks. We call this symmetry SC3 group, and it is special Euclidean transformation in 3D space. Also, sharpness is close to Locker's property since it strongly depends on the neighborhood points.
Yeah.
Therefore, we can think SC3 equivariant neural network can do this task well. Our main candidate is then SC3 transformer introduced in URIS 2020. SC3 transformer make use of relative coordinate between points, which automatically guarantees translation invariance. Therefore, we need SC3 transformer as rotation equivariant layers. We want rotation of input induces rotation of hidden layer outputs. A hidden layer has arbitrary dimension vectors. Therefore, we need to study group representation of 3D rotation, which is called S03, special orthogonal group. This is group of 3 by 3 orthogonal matrices with determinant +1. Group representation of SO3 is a well-known problem, and this can be easily derived from spherical harmonics. There are one representation per each 2L plus 1 dimensions, which we call degree L representation. These are same thing with the electron orbiter, which appears in quantum mechanics. For instance, degree 0 representation is scalar, which is invariant by rotation. Degree 1 representation is dimension 3 physical vector, which rotates in scalar way. For higher dimensions, please refer to original paper about SC3 transformer. Here is the detailed architecture of SC3 transformer. SC3 transformer first makes K nearest neighborhood graph and get relative functions as input. Secondly, for using layer, they get SO3 equivalent weight matrices. Spherical harmonics represent SO3 representation. Clap-Gordon coefficient reference map between representations. And radial relation is the lower part. Each input and output of layers consists of blocks with multiple degrees of representations. And weight matrices defines map between such blocks. Finally, like representation networks, they propagate queries, keys, values to adjust and aggregate as attention. The whole procedure is therefore rotation equivariant. For our task, 2048 points are randomly sampled from reference mesh. Then, for input of SC3 transformer, Kn graph with K equal to 20 is formed. SC3 transformer utilizes only K nearby neighborhoods as input, so if we sample more points or less points, input distribution will shift. To fix this problem, we normalized coordinate scale that the set of lengths of the edges have distribution of mean 1. Coordinate translation or rotation augmentation does not affect this model, so we did not do such things. For training objectives, we use two loss terms. First term represents probability of each point of being edge point. If the point is near to sharp edge, the probability becomes higher. To make this true, ground truth is set up as minus log distance to nearest edge. During training, 500 reference points are sampled from edge line set, and distance to the nearest sample point is calculated. Although these quantities may not form real probability distribution, this can still represent a reasonable quantity of constituents. This term is scalar field of Euclidean space. Second term represents offset to nearest edge point, and this is vector field over Euclidean space. Therefore, first and second terms are closely related. The second loss term is more important if it is close to the sharp edge. In other words, if first term has high value, the second objective affects well. Therefore, this is weighted by first term, that high confidence points are more affected by the offset term. Since the two objectives are closely related, single network will predict two values simultaneously. We weight loss terms by weight 0.5 and 1.0. Point-wise weight for second term is given by logistic function of the first term. The final loss term is as following: mean of two terms over point. At the inference time, top 1024, which is top 50%, confidence points are selected, and offset is summed to the coordinates. Next, k-NN graph with k equal to 3 is formed, which is organized into the edge graph by deleting duplicate edges. These are some inference samples. Rather than just selecting top 50% confidence points, it would be great if we find better way to filter high confidence points. Thank you very much.
Okay. I'm unmuted. Unmuted. Okay. So that was the presentation of Yusong Lee from Minds Lab and his solution to challenge 3, which is a new challenge here in Sharp. I'm looking at the chat. There is no any comments or questions. Maybe if we move to the next presentation of David Bojanic from the University of Zagreb, where he will describe his solution to challenge 1 about human body scans and the recovery of partial textured body scans.
Okay, so hi everybody, my name is David Bojanic. I'm a PhD student at the Faculty of Electrical Engineering and Computing in Zagreb. And today I'd like to present you our solution to the Sharp 2021 challenge. So briefly, the goal of the challenge was to reconstruct a full 3D textured mesh from a partial 3D human scan. So here we can see an example from the training data. So this was a full mesh that was given, and this is a partial mesh with generate calls on it. So our approach to use the 3D coded network from the 3D coded paper that is initially created to find correspondences between 3D human bodies. So the networks looks like this. So this is an input 3D point cloud that goes to an encoder, which outputs a latent code. This latent code or a feature vector gets concatenated to every point of a simple template body model that goes through a decoder that tries to deform the template into a point cloud that is the most similar to the input point cloud. So the simple template, as you probably already know, is a parameterized human body model that has around 80 parameters. So some of them are for the pose parameters, which are regulated by angle axis parameters for the joints, and some of these are for the shape parameters that are actually PCA weights for the PCA components that were trained or from real data. So here we don't actually use the parameters, but we only use the point cloud PCA. Okay, so the encoder part of the network is actually a point net network. So it has 3 multi-layer transitones that are applied to every point, after which the maximum layer is applied, and then 2 fully connected layers. This, as I've said, results in a 1024-dimensional feature vector that then gets concatenated to every point of the simple template. Okay, the coder part of the network has 4 multi-layer preceptons that are again applied to every point, and dynamic activation function at the end. So the training data used was simple models that on which we generated calls. So the pose parameters used were from the CMO mockup database, and we wanted to use real pose parameters. The shape parameters were from the Caesar database, and the calls were created at random whilst learning and with a dropping rate from 0.3 to 0.7, so 30-70% points per drop.
Okay, here we can see some example of the training data. So we can see that our part of the data is actually missing. So here we see we don't have the left, and here we actually don't have neither the leg nor a part of the chest or arms. Okay, so we trained for 50 samples. We used the Adam optimizer with this learning rate, and the loss was the mean squared error. Calculated between the input points and the output points, and we knew exactly which points should correspond to which point because we had the simple model inputs and we predicted simple model outputs, so we had the same number of points. Okay, so for the inference, there is an additional step where we optimize the latent code with regards to the chamfer distance. So the chamfer distance is actually the distance from one point cloud to the other by using the nearest neighbor distance. So we optimize that distance. So this reconstruction gets us close to the input reconstruction by optimizing these latent codes. Okay, so we had other approaches in trying to solve this challenge that didn't showcase any better results. So we tried to replace the PointNet encoder network with the PointNet++ network. We presume that we didn't get any better results since the PointNet++ uses a lot of local features that are not as reliable when you have when there are holes in the input data. We tried to replace our training data with the CAPE and the treated body data sets that had holes or didn't. So the CAPE data sets is a method to generate flows on simple models. So we generated flows on the same simple model that we actually used for the training as the training data. So this is an example of the CAPE datasets, and we clearly see less detail than an actual simple model, since the flows should be over this human body. We can also observe the outlines of the flows. The other dataset, the Cherry Body Tech dataset, is the dataset that we actually got from the challenge. We also try to replace the mean squared error that we used for the loss with the chamfer error, as well as the two regularization losses, the Laplacian and edge loss. So the Laplacian is an operator that works on a single point cloud, and the Laplacian loss tries to minimize the curvature around a point, and that same point in the input cloud. The edge loss tries to minimize the distance from two connected points as to be the same as the input point cloud. So here we can see some of the reconstructed submission data examples. So the first and third column, we have the input point clouds. And in the second and the fourth, we have the reconstructed point clouds. So we can see that the algorithm actually predicts the pose very well. So in here, we can see the hands are predicted well, and here the hands as well as the legs. The shape is a little bit bent, but that is mostly because we optimized the chamfer distance as an inference step to minimize the error, and that creates actually shapes that don't resemble that much humans. We can also observe here that the clothes can be also predicted, since this human is wearing something like a dress, and the algorithm predicted something resembling this. Okay, so to conclude, this proposed solution does work, but we have to note that the submission dataset is actually very hard to predict and to extract. And thank you very much for listening, and goodbye.
Okay, great. So that was the presentation of David Bojanic from the University of Zagreb. Is there any questions in the chat? So if there are no questions, maybe we can move to the next finalist, who is Ksenia Shcherenkova. Ksenia, so she will do a live presentation. So we are done with recorded presentations now, and the remaining three finalists will be having a live presentation. The floor is yours, Ksenia.
Yeah, thank you. Let me share my screen, please. Can you see it?
Yes, but we see the PowerPoint stuff. Now, yeah, we can see it. Great.
Okay. I will explain everybody the solution which we produced for the challenge 3, which is about the recovery of sharp feature edges in 3D objects. And so basically, we introduced the joint detection and parametric inference of sharp edge features. Sorry. So the idea is in the input you have the scanned object, and you need to predict the sharp edges in the form of line sets and also recover the 3D model, but in such a way that you recover the sharp edges and the rest of the model should possibly remain unchanged. So we have the CC3D dataset, which has pairs of CAD models and virtually scanned counterparts. In total, we have about 50K models, which are split into train, test, and evaluation splits. As you can see, there are 35,000 models in the train split, and the evaluation split was shared afterwards. What is interesting about this CC3D data set also is that it has objects of unrestricted categories with a complexity varied from very simple to very high. And also the typical resolution of the scans is on average more than 100,000 faces. So these are heavy meshes. We have the ground truth labels extracted from the CAD models, which are our sharp edges, and also the filtered version for the scans, which were where the inner parts which are not visible during scanning were filtered out. So the solution goes as following. First of all, we convert the input data into the intermediate representation, which is in our case a point cloud with labeled edges and the offsets. After that, we employ the edge detection network, which predicts the edge points and also the offsets. After that, we do the parametric inference of the edges and finally recover the sharp models. I will go into a bit more details of each step. So first of all, we did the relabeling and reformulation of the input data in terms of the point cloud. The edge points for each point cloud, which was sampled from the original mesh using Poisson sampling, they are labeled based on the margin distance to the edge points, which was selected as the 5% of the diagonal of the bounding box of the model. We find it the best. Each point also, for each point, we also calculated the offset vector to the closest edge feature. So after that, this data, which is now point cloud with 24,000 points, becomes an input to the detector network, which is comprised of point voxel encoder and the two heads, the one which predicts the edge points, and it uses the focal loss, and another prediction head predicts the offset points for each input point, which uses the offset loss, which is I will tell about a bit further. So the point voxel encoder was chosen based on the following reasons. Since we are dealing with a very high resolution meshes and we would like to preserve the details and tiny features, we need a memory and computational efficient backbone for network. So the point voxel basically uses consists of two branches, the one which performs on the voxel setting and another one on the point setting. The voxel branch has three main operations, voxelizations, convolutions, and devoxelizations. This is memory efficient architecture for training and inference as well. And we were able to train with a maximum voxel size of 64 voxels. We also extended the input features to include not just the points, but the normals, and we'll see some improvements further. So the focal loss was chosen from the consideration that we need to deal with the huge class imbalance due to the fact that the number of edge points is quite small in comparison to the overall number of the points in the point cloud. And the offset loss is a simple L2 loss between the predicted offset vector and the ground truth. The total loss is the combination, is a weighted combination of those two losses. So the idea of predicting the offset is the following. So since we do the labeling of the edge points based on the margin distance to the closest edge, those points, they're not guaranteed to lie directly on the edge, and the offsets were applied further to the ground truth point cloud to force the points to lie on the edges. And as you can see in the example, it gives quite a good result in strengthening the lines and then also grouping the points around the circles. The inference of the line set, it goes as follows. So we apply the predicted offsets to the original point clouds, specifically on the predicted edge points. We build a proximity graph based on the two nearest neighbors and the distances between pairwise points. And we select the average of such distances within also one STD. In this graph, we are looking for the connected components, and then each connected component is a basis to fit, to parametrically fit a line. Thus, on the right, you can see the final predicted edges in terms of fitted parametric lines. So the typical edge smoothing function for each scanner can be approximated with the following assumption. So on the right here, you can see the sharp angle and then the smoothed edge. So the smoothness of the edge can be related to the radius of the fitted surface and also the distance from the center of this surface. So having parametrically described our edges, what we can do is to project the nearby vertices from the mesh onto these edges. This way we do not harm the rest of the scan, but we also sharpen our edges in the locations we have predicted. So in the example here, you can see the scan, and in black and red, you can see the fixed sharp edges the way we offered. And here you can also see in black and red the fixed meshes with sharp edges and the scans. So as you can see, the edge detector generalizes quite well to different kinds of objects. But if we look closer at the proposed solution, actually what you see here is an overlay of the fixed mesh based on the line sets we predicted and the initial scan. So you can see that the lines predicted this way, they are piecewise linear. And this gives us quite a lot of artifacts since we have a lot of disconnections between the edges. And also we did some kind of ablation study, and see here you can see the results of the edge detector and the metrics in terms of accuracy, recall, and precision. So when we start with the basic point voxel network with resolution 32 and only the point coordinates as the features without the offset losses, we see quite moderate results. And going further, we increased the resolution of the point voxel network, and we also added the offsets in our losses. After that, we extended the features to include the points and normals. And the last step, the training was done not only on CAD models, but it was also fine-tuned on the scans themselves. So the overall accuracy on the evaluation set is 83%. Though the edge detector seems to be working quite well, we see some failure cases, mainly connected with the way we build the line set. So you can see a lot of false edges on the threads of the screw on the tightly connected components, meaning that we need to improve the parametric inference of the line set of our edges, and for this we need the segmentation further. So this would be the next step of the work on the sharp edges recovery. And I thank you, and yeah, that's it for me today.
So are there any questions? Maybe here in the room or in the chat? No? No questions. Yeah, just okay. A question from my side, Ksenia, please. The artifacts that you had in the edges using the line fitting part, how do you expect, like, how do you see that you can solve this problem?
The plan is to predict actually the segments of the different lines as a part of the network architecture. And this way we will obtain more connected points in one segment, and this will produce better fits for the lines.
Okay, thanks. So no more questions even in the chat?
No, Julien.
Okay, so maybe let's move to Julien. We're starting to be tight on time. So thank you again, Ksenia. We move now to the next finalist, Julian Shiban. And your webcam is turned on.
Finally. Hi, everyone.
Welcome again, Julian.
Welcome.
The floor is yours.
Thanks. I hope you can hear me.
Yes.
Perfect.
Even though we have some problem. Yeah, no, it's fine.
It's fine. Okay, great. Let me see if I can share my screen properly. So can you see screen right now?
We see yes, now we see your slides.
Okay, perfect. Okay, so hi everyone. Really excited to be back here. Second Sharp challenge, right? Yeah, let me explain a bit what we did for the Sharp challenge. Yeah, the surface reconstruction of IFNets you already heard from Gerard, at least if you attended the talk, everyone. But what he didn't explain so far was how to also do the texture completion part. And that's what we did for Sharp, for the last Sharp challenge. And yeah, I will go a little bit into the details of what we did there in order to complete the texture as well as the geometry, which was coming from the previous IFNet. But I will talk just briefly about that, and then I will go a little bit on the details on what we did differently on this Sharp challenge. All right. So first of all, of course, the question was, what is a good output representation for texture? Because we have to predict not only geometry but also texture. You could, of course, predict voxels and colors on top of voxels, but these, of course, have a very high memory footprint, so you will be restricted to low resolution voxel fields, which is not really what you want to have. You want to have a continuous and complete surface, right? So then, of course, you could have a texture atlas, but as Gerard also mentioned, having a UV parameterization of your surface is oftentimes ugly, doesn't really generalize to novel objects. You have to have a template, and you have this bad discontinuities, which often lead to surface to texture bleeding, right? Which you don't want to have. So that's why we explored this texture field representation, where you basically have one point in 3D space, and for that point, which is of course a surface point, you predict the color at that point. And if you can do that, you can do that at basically at arbitrary resolutions, at arbitrary points, which gives you, which frees you from the discretization that the other representations have. And you don't need any template because you can do that for any point in 3D space. So you're free of a template. So that's really the upside here, right? So that's why we work with this representation. So the first step that we have, and I hope you can see my pointer here, the first step that we have for solving the challenge is, given the input, we do a completion of the input surface, so only surface, no color here, using the simple IFNet architecture. That's exactly what Gerard already mentioned. And then what we do is we condition the texture generation on both, on the partial textured but incomplete input, and the full geometry, which is of course not textured, such that the texturing network afterwards can basically condition on both. So if the geometry reconstruction also has an edge, for example, as a T-shirt, texture completion can incorporate this knowledge. What is done there, it's basically the IFNet architecture. So we encode both inputs using a 3D convolutional network into feature grids of local structure until very global structure, which is similar to a 2D CNN. And then for each point, we want to predict the color, right? That's this texture field idea. And we do that by just extracting features at the location of the point from the feature grids that the neural network created. We then just concatenate all these features. And these are then used as basis to predict the color using just a fully connected network, which then spits out RGB values. And this then should be the completion of the texture. And the loss is quite simple. This is the output of the neural network at the point P, given the inputs X, and it should just predict the RGB, the ground truth RGB that we have from your really nicely textured scans. And we train that loss over multiple points. So we sample many points on the surfaces of the ground truth shapes. And we, of course, do this for multiple shapes because the data set has, I don't know, 2,000 scans or 3,000 scans, something along those lines. And yeah, we just do that for all the training samples, right? Okay, and the results, they were pretty nice. We've seen that, yeah, the geometry reconstruction did not only a local job, but they also predicted like a full missing arm and things like that. We were really surprised and happy about that. And even also the texture did a good job. It did quite smooth, but still reasonable texture completion. But of course, there's also a problem here, and that's the problem that we want to tackle. So the problem is that even though we have some details in the input from the texture, some patterns like those, our reconstructions from the previous challenge, they did not have these textures. So our idea was to basically not lose these input details so much anymore. And the way we wanted to do this is basically the following idea. So it's a very simple idea, but it's still powerful and needed to be done, I think, in order to improve. So the idea was basically to reuse the information that we have from the input and incorporate them to the output. So that's a very simple trick. And the basic idea is we take the input, we have the reconstruction, and from the reconstruction, we want to remove those parts that we already know from the input, right? Such that we basically merge the input and we only append the reconstruction at those locations where the input is incomplete, such that we can have the highly informative input, the nicely textured input, and the reconstruction, which is a bit smoother, only at the parts where it is necessary and not everywhere. All right. So, and here's how we did this in practice. So basically to subtract, the first step is, of course, we want to subtract the regions that we have in the input from the reconstruction in order then to incorporate them later on. So the first thing is we subtract basically the input, and we do this by basically removing all the vertices of the reconstruction. So all the vertices on this reconstruction that are very close to the input, so geometrically close, we want to remove those, right? And if they are close enough, so we have a threshold there, if they are close enough, we remove. So then the question arises, what threshold would be sensible, of course. So if we take this threshold around 1.5 millimeters, we see that we still have a bit of noise here because the network predictions are a little bit off. So they are off by 1.5 millimeters here and there. So we get noise, and we don't want to have that noise, of course. So what we do is we just use a larger threshold, which removes the noise. So we have some segmentation of, so basically this gives us the reconstruction, so the smooth reconstruction, but without the parts of the input. Okay, but of course that's a bit problematic still, because we removed too much, the threshold was too high, which means that there are missing regions between the input and the reconstruction. So we get some seams here that are not really nice, that we want to get rid of. We see that already, okay, we can incorporate the nice information of the input, and the reconstruction is also there, but yeah, we don't want to have these seams here so much. So the next step that we incorporated is for all these points that we have on this cutout reconstruction. So that's our reconstruction here, where we cut out the parts of the input. Now we want to expand those regions of the cutout reconstruction here. We want to expand those by some amount, by the same amount that we cut off previously, and basically expand them by the full reconstruction. It's just that the seams are a bit basically removed, right? And if we do that, we actually find that this really works well. Here you can see that yes, if we have this this cutout part where we have the threshold, but also we let the regions grow a little bit, that this really fills the seams, and we get a nicely a nice reconstruction that incorporates both the knowledge that we have from the input as well as the completion from our reconstructions. So that's what we changed for the submission. Here we can see this a bit in a larger scenario, a bit zoomed in, so we can really see. So the right side here is, of course, the thing where we merged. The left side is the reconstruction without the input, and we can see that we can retain more details of the input in this fashion by fusing what we have in the input. Here are some further results where we can also see that we can basically retain more information of the input by just fusing our reconstruction with the input that we have. All right, and if I got some time, but you can tell me at this point, if I got some more time, I would go over our current CVPR paper, which is quite related to what I just said and this sharp challenge. But if we were a bit tight on time here, we can also leave this.
Sorry, Julian, we would be happy to hear about your paper and so on. But the problem is that we still have finalists to present.
Sure.
And then we need to announce the results to be good on time. But thanks a lot for already your presentation and for proposing also to present your paper. Maybe just if we look at the questions, no questions at the chat. No. Okay. Maybe a small question from my side, Julian, please. I saw the black stuff actually, and
The seams,
that you fix it with some kind of a threshold, right, to grow up these regions. What about dilating these regions of the texture?
Dilating in the sense to have the regions larger, or what's
No,
your...
like do some kind of smoothing of these regions so that they got mixed with other colors.
I see. Yeah,
It
that
will
would
get
also
smoother.
be... Yeah. So what would be possible, I thought about this, is instead of just growing the regions of the cutout reconstruction, you could also take basically this scene, or this human with the seams, right, with the missing parts, and then just use a classical method, surface reconstruction method that basically first starts to fuse both these meshes, right? So you have the mesh of the input, and you have the cutout reconstruction. You use a classical method to fuse both meshes, and then you could use the texture field to color all missing vertices, and like that you would get a smoother and more connected mesh. That would be definitely a good step, yes.
Okay, thanks a lot, Julian, again. So now let's move to the last finalist. So it will be me presenting.
This one.
So I will be presenting 3D Booster 2.0, which is an improved version of the 3D Booster method that we proposed for last Sharp version at TCCV. So the outline of the presentation will be as follows. I will just introduce a bit the problem, then talk about the proposed method, that just recall the 3D Booster method, and then I will talk about the improvements that were made, the slight ones that were made in order to make the 3D Booster method better. Then I will show some qualitative results before drawing some conclusions. So raw scans are usually partial in real-world applications. This is due to multiple reasons, for example, self-occlusion or human motions, also to partial acquisitions, especially with handheld scanners. And the problem is that when we acquire scans in general, if we had some partial shape regions, we will also have some partial texture regions that correspond to the missing regions in the shape. So partial scans always come with a partial shape and a partial texture. So the problem here is that given a partial textured body shape, XP, we would like to recover a full textured shape X that is composed of a shape S and a texture atlas T. And by recovering the shape and the texture atlas while also knowing the UV mapping, we can have a complete textured body shape. So the proposed method 3D Booster is a sequential model. So we don't solve both problems, shape and texture completion at the same time, but we firstly solve the shape completion problem, and based on the solution that we had for the shape, we transfer the texture, the partial texture, into the completed body shape. By doing so, we will have a complete body shape, which is with the texture with a partial texture mapped on it. So that, as you can see here, I don't know if I can use the pointer. Yeah, you can see here the texture that was transferred in the complete shape results in some black regions on the shape that need also to be recovered. So the good thing is that by doing so, by transferring the texture on the complete body shape, we'll be able to know what are the missing regions on the texture atlas. This is not possible because, as you can see in the first texture atlas of the partial textured body shape, there are some texture charts, but they are. I mean, the partial regions are also mixed with the background of the texture atlas, so that you cannot know what regions are missing. So by transferring the partial texture on the complete shape, we can directly know the missing regions, and we can create a mask of missing regions. So having a texture atlas with the missing regions, we can do some kind of classical standard texture in painting. I will go into more details about the proposed method. So for the shape completion, we opted for an autoencoder deforming a template mesh. So the encoder consists of a simple point net, and the decoder is an MLP that will deform the template mesh. So using this autoencoder, we will obtain a rough estimation of the complete mesh. And then this rough estimation is then refined using chamfer laws in order to obtain the complete mesh. So this is borrowed from the 3D coded paper, which already which was presented for solving 3D correspondence between body shapes. So once we have the shape completed, here we can do some kind of classical raycasting in order to transfer the texture into the complete body shape, and then we will obtain a complete body shape with texture with partial texture mapped on it. So as I already mentioned, if we map the texture on the complete body shape, we'll be able to identify missing regions as shown here in red. And these can be used as masks for texture painting algorithm to recover the missing regions. So for the texture in painting, we considered a state-of-the-art method based on partial convolutions for image in painting. So this method considers partial convolutions on the missing masks in order to complete or impede the texture. So the partial convolutions are allows us to not consider some pixels in the neighborhood by putting the mask on the convolution operation, as we can see it in this formula. But then the mask is updated after each convolution so that it will disappear at some point after a sufficient number of iterations. So this method works well in texture and painting in general, but in our problem, in our data that we are having here right now, it's a bit challenging. Is because we have this background that can be diffused in the texture. So what we have is that we have a mask for the missing regions, but we do also have some background that we don't want to include in the texture and painting process. So to overcome this problem, we proposed some modification on the partial convolution for in-painting method. And this is done by including some background mask, which is computed directly from the complete body mesh. So we know that all what is in black is to not be included in the convolutions. And we include this background mask as well on the in the partial convolutions. In addition to the mask of missing regions, what we do is we fix this mask to not be updated. So this is not the case for the mask of missing regions, because we want them to disappear at some point, but we want to keep this background mask fixed along the texture in painting. So now we'll move to the improvements that were made to 3D Booster, the previous version in last Sharp edition. We started by, okay, let's see what are the limitations of 3D Booster 1.0. We know that we use an encoder-decoder network that was trained only on complete meshes. Here, a straightforward direction is to train on both partial and complete meshes. And also another limitation consists of the texture atlases that were that contained too much charts, and this may cause, for example, having a missing region covering a whole chart, for example, which is here in the case in the red region. So we made the texture atlases with less number of charts, yeah, normally we expect having better results with this kind of texture atlas. So here I'm showing some qualitative results. In the from the eval set of this Sharp edition. So here I'm showing some samples from level 1. In the first row there is the input, and the second row there is our predictions. So normally level 1 is less challenging than level 2, which is reflected here in the results that we are obtained. So to conclude, we use a 3D Booster method, which is a sequential method to recover both 3D shape and texture. The 2.0 version of 3D Booster improves the shape and texture completion. To draw some perspectives, we can think about making the shape completion better in terms of robustness to various poses, and especially large clothing that we noticed being like real problem in the shape completion. And finally, it would be great if we can make the whole networks and train them in an end-to-end manner. But here we need to be careful about the non-differentiable steps, like, for example, the texture transfer and the shape refinement. Thank you.
Thanks
for
a
the
lot,
great
Denise.
talk. Can I ask you a question?
Yes, please go ahead.
Cool. In the prediction, I saw some black regions.
Yes.
Of texture.
This is why I asked you the same question.
Can you?
Actually, these black regions. Okay, we had. I can show some, or you already switched my. Okay.
You want?
Yes, yes.
Please. Okay. I was talking about the impact of the texture background, and basically this is what we get. It's a result A. So this is the best that we can have without the background mask that we added to the texture and painting method. But still, even with this texture and painting, and especially when we changed the the texture atlas with less number of charts. So when we have, like, for example, big holes, like a whole region will be erased from the texture atlas. So it's still difficult to the network to know how to embed these regions.
But I would expect to then the network to put out, I don't know, an average color or something and not black. Black seems to be not really the average color, or am I not understanding it here?
Okay. You mean for the...
For the, yeah, there are some black regions, right? And so I guess, like, if the network has a problem completing, I would expect the network to complete with, I don't know, something brown, or I don't know, some average color. You see my point?
Yeah, I see your point, but to my understanding, I mean, for the partial convolution to work, I'm not talking about the background mask that we are adding, okay? I'm talking about the mask of the missing regions. The basic idea is that this mask will get smaller and smaller until it disappears completely. But here, obviously, the holes were too big, I guess. The holes were too big, so that the network was not able to make this mask smaller and smaller and disappear completely.
I see,
So
okay.
this is my explanation and also intuition. I did not have like a lot of time to really make like a lot of experiments, but this is my intuition.
Yeah, makes sense. Makes sense. Okay, yeah.
Thank you for your question, Julian.
Thank you. With that, we have finished, I believe, all the panelist presentations. Thank you to all the participants. And now it's your turn, Ksenia, to make someone or some people happy.
I'll try. Thanks. So I guess I'll share my slides. Are we good? So yeah, let me do the honors on behalf of the RTEC to announce the winners of our Sharp edition 2021. First of all, I would like to thank everybody who was involved in the organization and those who participated and made this event happen. Thank you so much. And I will start with a small showcase. And we call this HD mode. Maybe some of you heard of this. So basically what you see now, it's a new feature we announced recently at RTEC 3D. And this is the scan without HD mode enabled. And you can see the magic happening on the bottom, where we can see the intricate parts of the engine. One more example of the HD mode on, off. And here you can see the sharp edges of the hubcap. The next one, my favorite, the skeleton without HD mode, and you can see basically like through the insides of the skeleton. So the thing here that HD mode is not magic and just a 3D reconstruction technique where we employed the deep neural networks. And just imagine that having for the last 10 years your 3D scanner, and with a software update, you get exciting new technology. Of course, it involves tons of research, a lot of new features were tried from deep learning and other techniques. So that's why we love research, we support research, and we are getting back to the challenge. So in total, 3 challenges at Sharp, 3 new data sets, and finally we have 4 teams submitted the results. I will go directly to the score table. And as you know, this year we were announcing the total price of 9K euros, which was supposedly to be split equally between 3 challenges. And we decided that we will do the prizes for the first and second place. And in any case, you can see in the table that the only participant who participated in all the challenges was a 0 baseline. So everyone below the 0 baseline will not get a prize. So, ta-da! Here are the winners for the first challenge. This, just like the last year, the MPI Max Planck Institute for Informatics, the first place, and the S&T, the second place. The second challenge, the situation is the same and a bit different for the third challenge. So the S&T got the first prize and the Minds Lab got the second prize. Congratulations to every team participated. As usual, the S&T team will probably not get the money, but will hope to get some new GPUs as equivalent for this year.
I need to mute.
So, congratulations.
GPU is good.
GPU is good.
I think
Congratulations.
we can go for the
Congratulations,
coffee machine.
Julian.
Yeah, thanks a lot. Thanks a lot.
Congratulations.
It's super cool.
Congratulations. Well done.
Thanks.
And come back next year.
Sure. As long as the challenge is running, I will just keep hitting the same nail.
We'll do something better next time, probably.
All right. Congratulations also to the S&T team. Congratulations to Minds Lab. I don't know if we have Young Song here with us. I think not. He did.
No,
Let's see.
he's not attending.
No. But we will communicate the good news to him. And congratulations to everyone. And now we should look at the results in more
Yes.
detail.
Exactly.
Evaluation and results.
Have another presentation.
Thanks a lot for making this possible, of course, right? For
So-
organizing, and that's like super great. I think the challenge is really relevant. You see this also that, yeah, it's a hard challenge, right? Not so many people are submitting like these good results so far, because I think that's it's not so easy, right? And that's because it's an important challenge that people need to address. And I think, yeah, if you keep doing this, the results will keep getting better, and people will realize that this is a really cool and important thing that you're doing there. So yeah, I'm really excited, and I like the challenge, and yeah, thanks so much for organizing.
Yeah.
Thanks, Ian. Congratulations. I do think that people find it challenging because from the start of the registration, I think we had more than 59 participants, and then as we get closer to the submission deadline, then we have less commitment. I think because it's challenging, but
Yeah.
you're the proof that it's worth it.
Definitely, yeah. So thanks again.
Thank you.
Okay. Shall I start, Jamila?
Yes,
Okay.
we are very late in time, but but go ahead.
Okay, so should I go fast or
No, I think
use the planet time? Okay.
I'll tell you when to speed up. Go ahead.
Talk about the evaluation and analysis. So how, for example, Junior won the prize, and how the SMT team also won the prize also for Challenge 3. So I'll describe a bit the metrics and also detail some, provide some detailed results about these findings. So the outline of the presentation will be as follows. I will start by an introduction of the challenges in the dataset and also show some evaluation samples. Then I will talk about the evaluation metrics of challenge 1 and 2, which are pretty the same, but for challenge 3 we introduced a new metric, and I'm going to talk about also this metric. Then I will talk about the analysis of the results with a detailed analysis on the separate challenges before concluding and also giving the floor to the panel discussion. This Sharp edition, as already mentioned by Jamila, we had the same 2 challenges as last year, but we added 2 levels of difficulties. So we added by levels of difficulties, I mean levels of partiality. So we provided more partial scans as for level 2, but for level 1 we kept the same parameters as for last edition of Sharp. Then there is this new challenge 3, which is about recovering sharp edges in object scans. And here the task is to, given an input scan, is to recover a set of sharp edges as line sets, and also approximate the corresponding triangular CAD model in triangular mesh. So here some samples of from the evaluation set, so that were used to evaluate the methods of the participants. So as already mentioned, there is this level 2 where we added some difficulty, and here is an example of the input scan and also the ground truth edges with the CAD model for challenge 3. So now I will move to the evaluation metrics, and I will start by the metrics on challenge 1 and 2. So challenge 1 and 2 is about recovering partial textured scans, and the idea is to estimate textured complete mesh X, which should approximate a ground truth complete mesh Y. So here X is evaluated following 4 criterions, which are surface face areas, shape accuracy, texture accuracy, and also surface hit rates. So I will go quickly through these metrics. So the first one, which is the surface face areas, consists of a global measure to evaluate the amount of completion in X with respect to the ground truth Y. So to compute this measure, we compute the face areas of the estimation and the ground truth by summing over the areas of all faces of these 2 meshes. Then we consider the normalized face areas, which are provided by this AX bar and AWAL bar. And these 2 are then used to have the final area score. Here it's important to note that such score is asymmetric. So here, if we are having an area of face areas of the estimations that are greater than the ground truth, so we will not penalize that much these participants, but we will more penalize the participants that provided area scores that are underestimated. So then I will move to the metric of shape accuracy, and here we consider two directed similarity measures, one from the ground truth and to the estimation, and the opposite. These two similarity measures are approximated by sampling points as shown here in this figure on the faces like if we take, for example, the estimation, so we sample points on the faces of the estimations, and then we identify the nearest triangles in the ground truth mesh for each point using a point to triangle measure, and then we sum over all these point to triangle measures to have the similarity measure from estimation to ground truth. Then the same procedure holds also for the other direction. So for the texture accuracy, it's also the same concept, but here, after identifying the nearest triangle for each point in the, for example, the estimation, we identify the nearest triangle in the ground truth to this point. We will then use another function that will interpolate the color values in the point that was sampled, and also at its intersection in the nearest triangle that was found. Then we just compute the Euclidean distance between these two colors. So here also we have two directions, so the same procedure holds also for the other direction, so from ground truth to estimation. So we also added this surface phase heat rates, which correspond to some local measures that evaluate the amount of completion in X with respect to the ground truth Y. And here also we consider two directed heat rates, one from X to Y and the other one from Y to X. And this heat rate is just indicate the amount of points that are sampled on the surface of source mesh that will have a correspondence on the target mesh. And we say that the point has a correspondence in the target mesh if its projection on the plane of the nearest triangle intersects the triangle itself. So here are two examples of a hit and a miss, and we compute these heat rates having using these two formulas from in the two directions. So now, to have the final score, we will just compute the shape score, which is a mapping of the similarity measures using this function phi, which maps a similarity measure D to a score in 0, 1. And then this function phi is parameterized by some parameters k that are chosen according to some contacted baselines. So the same also for the texture score. We do exactly the same, and then to combine both, we take the average of these two shape and texture, and we multiply them by the surface phase area score to have the final combined score. I will now move to the new part of the metric, which is the metric for challenge 3, which is a bit inspired from what has been already done in challenge 1 and 2. So here I will come back a bit to the original problem that we had in the beginning. So we have an estimated enhanced scan, let's say, in terms of feature edges. And we have the ground truth cut triangular mesh, which is the ground truth. So we want our estimated enhanced scan to be as close as possible to the cut triangular mesh. And the other side, we want also to have the estimated sharp edges as line says to be as close as possible to the ground truth sharp edges. So here we will have two separate scores. We will have a shape score and we will also have an edge score. The shape score is between the shape scan and the enhanced scan and the cut triangular mesh, and the edge score is between the sharp edges. So for the shape score, we make use of exactly the same procedure as in Sharp 1 and 2, but we just discard the texture as it's not of interest here. Regarding the edge score, here we consider the edge lengths and also the edge-to-edge accuracy that I will explain a bit later. So here I will just come back to the shape accuracy. There are some important points to note is that for sure, if we will use the CAD triangular mesh as it is, this CAD mesh will have some inner parts inside that are impossible to reconstruct just from the surface of the scan. So these regions, we made sure that we filter them out before conducting the evaluation. So here is an example of the CAD modeling as a triangular mesh and its masked version. Another very important point is that here we add some points that are sampled around sharp edges. So, as I said in the beginning, to compute the edge, the shape accuracy, we need to sample points on some triangles around the shape. But here, as the interest of this challenge is to evaluate sharp edges, we make sure to sample 30% of the total amount of sampled points, and we sample them around sharp edges as shown here in this figure. And finally, the shape score is the same as I said earlier. Now I will move to the edge lengths. Here, the idea is borrowed also from the face areas. So it will be just a global measure that to evaluate the amount of correctly detected sharp edges in E prime with respect to E, so with respect to the ground truth. And here we compute edge lengths by summing over all lengths of the edges. And then we consider normalized edge lengths as already done for the face areas. Then we can consider this function, which has been used to compute the face area scores. But here, as I already mentioned it in the previous slide, this kind of function is not symmetric, and it will penalize. It will not penalize those who will submit edges, very long edges. So this is not the same purpose as for Sharp Challenge 1 and 2, because we were interested in partial regions, but here it's another problem. So this is why we built this piecewise function to make it symmetric and then having the same behavior for overestimating the edge lengths or underestimating the edge lengths. Then the second criterion for the edges is the edge-to-edge accuracy. And here we had two directed similarity measures that are similar to the ones that are used for shape accuracy. But here, instead of sampling on the triangles of the mesh, we will be sampling on the edge lines. And then identifying the nearest edge using a point-to-line distance and not a point-to-triangle distance. Then we sum over all the point-to-line distances to have our directed similarity measure. Then also do the same for the next for the other direction. Then here is an overview of all the combined score. For the shape score, we already know how to combine it. We did also the same for the edge score, and here we also map the similarity measures in the two directions using this phi function and and we trigger these parameters according to some conducted by baselines. The combined score is then finally the average of the shape accuracy and the edge accuracy and the edge score. I will now move to the analysis, and I will start by an overview. Here we had three challenges. We had, for challenge 1, we had 11 registrations. But when I say registration, is that they really went to the stage of having the data and so on. And we had also 3 submissions by 3 participants. Then for challenge 2, we had 9 registrations with 2 submissions from 1 participant. And finally, for challenge 3, we had 10 registrations, and finally 2 valid submissions by 2 participants. And here I'm showing the important scores for all the challenges and also per level. The 2 first blocks are for challenge 1. The very top one is for level 1, and the next is level 2. Then we have challenge 2 with level 1 and level 2, and then we have challenge 3. So as already announced by our colleague Xenia, MPI submission, Julian specifically, they had very good results on challenge 1, level 1, and also level 2. They reached around 90% of combined score. Just to give you a hint, for example, last year, I think they had 85% or something like that, 86, if I remember well. So yeah, here it's not the same portion of partiality, and also it's not the same parameters that were used to generate the partial scans, but it already says something. We can see also some improvements for the SNT method, that especially for level 1, but it's still struggling for level 2. The unmodified partial data were outperformed by both SNT and MPI submissions, but the submission of Unizagreb was beyond. That means that it does not improve the partial scans. For challenge 2, it was a bit more challenging than challenge 1 for MPI submissions, and for level 1 they got combined score of 75%, while in level 2 they got 62%, which is because the amount of partial regions for level 2 was a bit high. For challenge 3, the best score that was scored by SNT was 57%, with the shape score of 80%, but the problem is the edge score. That means that here they only reached 35%. That means that there is still work to do in these edge scores. So now I will conduct a more detailed analysis per challenge, and I will start by the scores distribution. So here I'm showing the box plots for the shape scores, the color scores, and the combined scores. We can see that MPI and SNT submissions improved a big proportion of the partial scans, and I'm also showing some histograms for the separate scores and then also the combined scores. As already mentioned, Unizagreb did not improve the shape scores, but they also did not provide texture prediction, so they only provided shape. And here another remark is that the SNT method improved color scores better than shape scores, and MPI methods highly improved shape and color by the same way. So it's kind of then for level 2, it's just here to show that it's more challenging, and we can see that especially for SNT and Unizagreb, which had much lower results. And now I'm just also showing some texture correlation texture and shape score correlation for the two levels, level 1 and 2. We can observe here high correlation for MPI submission, but less one for SNT submission, and this can be explained by the sequential method that they opted for. Here, very quick analysis about the poses. We can see from the histograms that non-standard poses were more challenging than standard ones, and by saying standard ones, we mean A and U poses. Then analysis of casual versus fitness clothing. So here we can also see that the casual clothing was more challenging than fitness, which is in both shape and texture, which makes sense since it's not easy to fit these regions. Here I'm showing the best and worst predictions per submission, we can really see the impressive results that were obtained by MPI submission, especially for the best one. So now we're moving to challenge 2. So here I start always by having the scores distribution separately and also combined. Here we can see that MPI submission also improved a big proportion of the partial scans in both shape and texture. And here we noticed that the two submissions for this level were having the same meshes, and we had the same scores. So maybe it can be due to some zipping issue, or I don't know. We can also notice this high diversity of the scores, and this can be due to the genericity of objects in the dataset. For level 2, we can see that is way more challenging than level 1 for all submissions, but still MPI submissions improved a big proportion of the partial scans in both shape and texture. Here also with the correlation between texture and shape that look higher for MPI submission in level 1 than in level 2. Here the best and worst prediction from MPI submission. I think the same object which was here, which was the worst prediction, that was the same last edition, I guess. Finally, I will move to the challenge 3 results, and here we are showing the box plots of different scores. We are showing shape scores, we are showing edge scores, we are also showing the shape scores near edges, near sharp edges. As I already mentioned in the metric, there is these points that were sampled around the sharp edges to quantify how the shape is reconstructed around these regions, which is the main purpose here. We can observe here from the score distributions that all submissions have almost similar shape scores and also shape near edge scores. But here it's important to note that we found out that MindLab submission contained just upsampled like row scans. But in terms of edges, there was something. So yeah, as I was saying, SNT and MindLab did better in edge score than the edges directly computed on the scans. So the overall score is better. And here an experiment is to see if the shape scores near edges, near sharp edges, are correlated with the edge scores. The intuition in the beginning is yes, but here we can see that there is no clear correlation between the shape scores near these edges and the edge scores for all submissions. We can just observe a better correlation for all submissions than row scans. This is good. But the highest correlation was observed for MindLab submission. Here, the best and worst predictions for both submissions, MySlab and also SNT. So, yeah, I think the best one was the prediction of this box from the SNT method. Not very far, let's say. Now I'll just conclude. So we communicated more than 100K meshes that were provided for training, testing, and evaluation this time. We had 7 valid submissions from 5 participants, and the range of all final scores varied between 5% and 90%. Here we dealt with 2 different problems: the recovery of partial textured scans that was evaluated by quantifying completion and accuracy in shape and texture, and the other problem is recovery of sharp edge features, which was evaluated by quantifying completion and accuracy in shape and edges. To sum up, challenge 3 was the most challenging this time. The best submission was less than 58%. Results of challenge 1 showed that some poses and clothing type were more challenging than others. Then level 2 in the 2 first challenges was more challenging than level 1, which makes sense. But yeah, here conclusion, I guess these are promising results, but we can still improve.
We can still improve. That's a good conclusion. Thank you very much, Anis. And now I think we can go right on to the panel discussion. I apologize to our panelists who have been waiting a bit. We're running late, but I think we'll make it. I would like to first start with Shohei Nobuhara, who is actually waking up very, very early for us. Shohei. Good morning, Shohei.
Good morning. In fact, it's 3 a.m. for me.
3 a.m. Oh my God, thank you so much. Shohei from Kyoto University, so you understand the time difference. I'm very grateful for you accepting to join us. Also, Gerard, who was here earlier, Ponsmol, and also Sylvia. I don't know if we managed to have you in.
Yes.
Yes.
Yes. Hello, everybody.
Hi, Sylvia.
Good morning.
So great to see you. So Sylvia Soufi, I don't know if I pronounce it well. Soufi?
Perfect. Yes.
Okay. From IMATI CNR, which is a research institute, if I understand well,
Yes.
right? And it's
the national is an institute of the National Research Council in Italy, and is the Institute for Applied Mathematics.
okay, great to have you. These are our guests who happen also to be the program co-chairs of 3DV of this year. And I thought, you know, these are the greatest panelists we can have for this topic, for the Sharp workshop and challenge, the experts on 3D computer vision. And of course, everyone is welcome to join. Ksenia is online, the room here. Anis, Mohammed, please do participate. You are our very skillful moderator, but do participate. And Julian, I think you're still with us. You are our Sharp expert.
Yes, I'm here.
All right. So I have a couple of questions just to guide a bit the discussion. Just a bit of introduction, especially for Shohei and Sylvia regarding the Sharp Challenge. So this is the 2nd edition. We had it last year in ECCV, and the main motivation really came from our body data that we collected over a few years that comes with high resolution texture. So we thought here we have what we believe is unique, because usually the texture that comes with body data is of lower resolution. So the question we had is, how can we promote using a 2D or texture with 3D data, and how the 3D and the 2D can help each other? Now, this was, you know, when we put the proposal to do the workshop, this was really, I think, 2019. And then the nerve representation came, and we see this explosion of using 2D with 3D and with a lot of potential, etc. So the question that I personally have is it is Sharp still valid? Is it the only representation, or is the door still open to what is the best way to use 2D and 3D together? That's first thought. I'm looking at Sylvia, who has big eyes, big, beautiful eyes. So go ahead, Sylvia.
I think using 2D and 3D is actually what I need, and I think what a lot of people maybe might need. So I work on a very kind of specific topic that is doing computer vision for animals. And most of the time when we see 3D works in 3D, we assume that our 3D objects are easy to scan. So we have all this human data with very collaborative subjects. But then it seems trivial to transfer all the knowledge we have for humans to animals. It's not really the case because we have tried scanning animals. It's really
brave.
We are trying, and you really have a lot of issues they just move, and you cannot scan the whole animal in one shot. And probably at MPI in Tübingen they have a lab where an elephant can enter, but in general you maybe can scan parts of the subject. And so I was actually looking at your challenges, and I was wondering, maybe there's somebody that can solve my problem of having partial scans that are capture with a slightly moving object, and you don't have holes, you just have parts. You have, I don't know, a leg and a piece of neck and all these other parts that you might stitch together. And what you might know, so a signal for stitching all these parts together can come from the texture. I think this your theme is really relevant for my problems. So I think this workshop should go on and provide a lot of solutions.
Well, you actually jumped right into my last question, which is the future of Sharp. You're basically telling us that, yes, there are applications that are very relevant. And I see Ksenia smiling. Ksenia, who represents the industrial partner who are looking for applications. Maybe, Ksenia, you can also comment on this very original application.
Yeah, from time to time we try to scan moving objects, not just animals, but small kids. And
yeah, I have those at home. I know what it is.
So this could be a good topic to follow in the future.
And in fact, I believe, Sylvia, you're going to, in half an hour or so to a workshop in CVPR that is right on animals, right?
Yes.
Sensing animals, something like that. So, yes.
Vision for animals. Yes.
Yes. So there is a whole theme in there, and maybe joining forces would be interesting with the other workshop.
Really.
Any comments maybe in here?
Yeah, I think, like, for example, the problem with the animals is you can use the handheld scanners, for example, which will not be accurate. So we will be in the same problem of partial textured scans. So
I live in the countryside, so I'm just thinking which kind of animal can be dangerous as well.
Yeah, but actually, sorry, go ahead.
Yeah, go ahead. I was about to go.
No, like that. This challenge of like shape puzzles can be quite interesting, right? So you have different images of different shapes. Could be animals, could be humans, could be objects, and then yeah, then the challenge is to put the pieces together. It's quite different than reconstruction. It's more what
Yes.
teaches to what and how, and yeah. So
Mosaicing type of thing.
so you have like so as I understand correctly, if I understand correctly, you see different parts of the animal and the animal is moving. Is that
Yes.
true?
Yes.
And from this you have to build the model.
Yes.
That's quite difficult, I would say. Yeah.
Yeah. Yeah. I think it also
because to estimate the pose, if you only see one leg, it's really ambiguous, right? How do you know the pose of an elephant if you only see the leg? That's not. Oh, it's almost impossible.
we're starting with more like domestic animals, but the most like the most exciting animals are actually the one that you cannot find because they're like a dangerous species, and these animals are not accessible. So the moment for this 3D to D, we're gonna focus on animals that we can reach easily.
No, I'm very serious about teaming up with the other workshop. I think there is something to do there. But we'll discuss it also with Artec. Maybe we can come back to a specific type of animal, humans. Just Shohei is laughing, but also with the challenges that come with sensing humans, especially what we call in the wild. And I'm looking here at Shohei, and I recall the congratulations on your best paper award for I think the workshop was on dynamic vision, right? Where
Thank you.
had and you had a simple model in there.
Yes. Yes.
Yeah,
Yes.
but
It
it
was
was outdoor. I recall seeing this repetitive motion. Maybe you can describe it for everyone and the challenges that came with it, with the data collection.
Right. Our idea was just looking at repeating motion, single motion repeated from observed from the different directions. Then we can use the repeating motion itself as the key to synchronize the videos taken from the different time samples, and also to calibrate the cameras. So with respect to that particular single motion observed from different directions and different time. So I think, for example, so in the case of Sylvia, for example, so if the target is doing, the single motion, for example, walking, for example, then I think we can make use that motion itself as a key to synchronize the videos and also recognize the viewing direction of the camera. Yeah. So, but in this case, we could do that because it's human, right? So we know the human kinematics, for example, and we have a very good pose estimator, 2D pose estimator. But I think to do that for elephants, maybe we need another one for elephant, maybe. Yeah, but in fact, so sorry, so I have another project that has underwater capture of the fish. Sorry, again, non-human stuff, but but in that case, so again, the fish, we could capture the fish, just a part of that, and the fish swims in front of the camera, and we integrate the shape in the thing, right? In that case, I think interesting thing is that if the target is moving, of course, it makes a difficulty, but also it gives us a good insight about the reflectance property of the target surface. I think, of course, it's a difficulty, but still, maybe in particular for example, the human clothes, for example, or animal skins or fur. So maybe I think it can be another, interest to recover or model the reflectance or surface, such as textures or properties, just not as just a single image, but a more complicated one. So I think that can be a good challenge, I think.
Yes, I had that also on my notes. And in fact, we're kind of converging to similar comments we had last year, I think also with Hao Li and David Fofi, talking about being specific to a given category objects or animals to make it even more interesting. So we are going into that direction, and the comments are going in the same direction. Indeed. We touched on the model. So if we have a known object, going back to the human body to simple, or even for the fish, the example that you mentioned. So there is, I think there's multiple attempts to merge nerve representation with the model also. Here, Gerard touched on that a bit also in his talk. Maybe you can also comment on that. What is a good compromise? And how should that model be? How generic should it be?
Yeah, so yes, it's true. I've seen a couple of papers and we also looked into this. So I think things that are very useful from the simple model are, for example, the fact that it encodes very easily that the humans move according to a skeleton and that parts move according to a kinematic chain. So relearning all this seems not necessary, right? So we have very simple equations, concatenating rotations. It works like really well. Now modeling things like, for example, like an opening jacket on top of the body.
Right.
Yeah, you model, yes, that seems to be better suited for nerve. And so we've seen nerve models. I mean, so I think now what this seems to, what's interesting is that we used to bring all meshes into canonical space and then do the statistics of the non-rigid deformations there. And now people are trying to do the same using implicit representations. So basically you bring like not only the mesh, but also the points surrounding the surface. You transform them and you bring them to canonical space where you then learn the nerve-based representation or implicit-based representation. And it's quite nice actually, because it brings some classical ideas to these new implicit representations. And yeah, I think in terms of the challenge, if you want to get more people, probably you need to have more image-based challenges. I think like a lot of people,
that's what we thought also.
Yeah, so basically like you have multiple images and then there you can already apply nerve-based techniques, or like you have one challenge which is from a single image, what can you recover in terms of shape?
Although I think that the community is becoming braver and braver into going into 3D, and you can see that in this year's CVPR.
Definitely.
Yeah.
Actually,
so, that this can be a sign that we'll have more submissions on 3D.
Yeah. I mean, one problem is also deadlines. I think people are really already overwhelmed, and it's difficult to find time for this. And the challenge is, I mean, for example, like Julian had the code and the method that is very suited for this challenge, and this was really easy for us to participate. But if you don't have it, it's of course difficult to adapt. For example, some people might have code to go from images to 3D. More people, I would guess. So maybe that's one way of attracting more participants.
But that was indeed the early motivation of Sharp, is that, and this is why we put, for instance, a use case in our 3DV 2018 paper, where we basically projected and created a lot of multi-view scene and then worked on the 2D images and then projected back, reconstructed. So we thought that people would do that, people working on 2D. So we offered that opportunity. But I think maybe pushing more explicitly into that by designing the tasks and the challenges that way. We kind of kept it open.
Right.
So indeed, it attracted you guys who had already a tool that was ready, which is great.
Yeah. Yeah, but it's true. There's a lot of people that also have, if you look at papers, they also have 3D to 3D, basically. Point cloud completion. And maybe I was thinking like, so I have several ideas for challenges. So So real problems are you have depth image, and there, like, it's very clear the kind of holes that you have. It's not like this simulated holes, but they are really like half of the shape is missing, and it varies according to viewpoint. And also occlusions, objects can occlude humans. These are also, for example, now you're occluded by the table, right? I mean, can I reconstruct human when I have heavy occlusion? So this would be also nice extensions.
Natural partial regions, right? Like,
Yeah. And the other thing in terms of analysis is like, how robust are the methods to rotations, for example? Like now take the results of one challenge participant and like rotate the shape and see how stable the results are. Because we want algorithms to be really robust to rotations and little like changes. And I suspect that these deep learning methods might not be as robust as we want.
Yeah. You wanted to add?
Like the perfect scenario is that we go for like natural scenarios and real world scenarios without synthetically generate these partial regions and so on. But the problem is that how you can get the ground truth afterwards, the exact ground truth to evaluate.
You can do the synthetic.
You're muted, Gerard, I guess.
We don't hear.
Sorry. Yeah, you're right. You can simulate depth data though.
Yes, we have our simulation expert right in here, Mohammed.
Actually, like from the work we did in human pose estimation from extreme viewpoint.
Yes.
Actually, you don't even need occlusion if you have view, which, like for example, you have like kind of views that don't see the feed. Most of the model actually kind of guess around from the data set. So try to kind of interpolate the data based on already existing data set. Nothing is that actually even have logic of how the human body should behave or something like that. So I don't think it will be kind of like direct cut, like you can just learn the whole thing, which make it good problem to work on, I think.
Mm-hmm.
And it's easier if it's synthetic. I'm just thinking of the extremely hard work of collecting data. That can be very painful. I think doing some kind of combination of synthetic and real data is a good compromise.
And render the scan.
You can render, and that's what we did. With the and now with the self-supervised learning, maybe there is potential to exploit that without having to go into hundreds of thousands.
So maybe what can be done is like you feed the simple model to the scans, and then you generate poses taking the AMAS data set or some data set of poses. And then you simulate these different poses, and then you simulate like depth data. And then the challenge is to reconstruct the full human given the depth stream. Because the depth stream, I mean, that's a real problem. Like you have a depth point cloud or an image, and then you have to reconstruct the shape.
Yeah, absolutely. I want just to touch on one extra point, which is actually inspired by challenge 3. Now we added this third challenge. Is about CAD data, basically. A lot of the works are on meshes, on these implicit representations. And now there are very recent works, and I checked also in CVPR, there's one nice work. It's called BRepNet. So it's working, so a deep neural network on CAD representations. And I think this opens a new field, in fact. There is also one on deep CAD that is not peer-reviewed yet. But this is a good opening, and also the ambition that we had by putting the CC3D data in there. So maybe Xenia can comment on that, on the openness of the field and what remains to be done. A lot, maybe everything.
Yeah, we are basically dealing with 3D data in in the form of triangulated meshes or point clouds, and the BREPs and the CAD data is like another level.
Yeah.
I mean, there are so few works there that might be too challenging.
Yeah, indeed, indeed. Too challenging, never. I think there is always a point to start from, and these couple of papers that just appeared are very exciting, and they tell you that the interest is there, definitely. I think from industry mostly, and I think it's definitely worth pursuing that. And this is why we added that challenge, third challenge. Which is different. Note the challenge. Sorry, Ksenia. There's a delay, I think. Just to complete the point for within Sharp is that the first two challenges we had texture, and it was about completing texture, and then we brought challenge 3 that doesn't have texture. And in fact, I was thinking that we need probably to change the title of the workshop and remove the texture from there, but still talk about recovery of partial data, because challenge 3 shows that it's the case, except that we don't have the texture in there. So maybe for edition 3, we remove the texture from there and keep it a bit more open, even if we have applications that are focused inside. What do you say, Julien? You did not attempt challenge 3. That's another PhD, right?
So I think, yeah, the models were prepared for challenge 1 and 2, so that was quite incentive to just go for those.
I know. But indeed, it's very different. That's why.
Yes, that's right. But actually, I thought about what one could do for challenge 3, but sticking a bit along the lines that of the methods that we have. And I think there is still something you could do, right? You could detect edges also in implicit space, and maybe with this, by predicting implicitly these edges, you might just have the same advantage again, that you have this higher resolution instead of doing the prediction in I don't know, in other ways, right? So that was something. So I thought about maybe just classifying if there is an edge or not, and then classifying densely the space, maybe then creating a line from the classified data, something along those lines.
Mm-hmm.
I think that would be interesting.
Those lines?
Along those lines, yes. But maybe to comment also on your very, very first question regarding, I don't know, 2D versus 3D, and if Sharp is really still relevant because now we have Earth. So I think it's maybe a bit of a boring answer, but as in many cases, it's not either or, it's a mixture, I think, right? It's 2D and 3D, and it really depends on, I think that was already discussed also, what you have, right? So for your specific application scenario, what do you have? Do you have 2D images? And if you have 2D, and many people focus on 2D images because that's the predominant thing we have, right? We have huge corpora of images. And I think that's also partially why NERF is now picking up so strongly, because people can fuse now the knowledge that they have about 3D and use it for 2D with 2D data. I think that's why NERF is so
popular and exciting.
Exactly. So all what we know from 3D, we can also do with 2D data. So I think that's key here. So I think what Gerard said, that if you want to have more participants for Sharp, if you include something with images, just 2D images, then this will definitely attract huge amounts of people, probably.
Yeah, I agree. Thank you, Julian. This is it's good to have also the perspective of someone who has been fighting for the challenge. Thank you very much. We have to conclude, and before we do, I would like to ask maybe Shohei to give some final words. Maybe what are your expectations for 3DV in view of the papers in CVPR, because we're also closing CVPR kind of.
It's very good point. So in fact, so yeah, as our 3DV program chairs team, so we would like to invite many papers about for example, how we can, for example, advance say now I think the 3D scan itself is getting a more like a traditional approach, right? So we need to somehow extend the field of application, such as, for example, the non-human stuff or non-regular, say, application scenarios, and also the dynamics, such as exactly as you say, that the 3D scans, but with of the subjects moving just a bit or moving too much, maybe. Yeah. Yeah, and also I think I think the sharp challenge is it's doing a really on the right way, I think. So it has a good challenge, and also it has a good open questions about how to deal with the drifts or textures. And also I think maybe we are also interested in reconstructing the surface properties, not only the geometry, but also the, say, photometry, maybe.
Mm-hmm.
So I think it depends on, of course, depends on the applications, but not only the point clouds, but the surface properties itself will be a good application for many researches. So in particular for non-human part, so animals.
Yes, yes.
And also CAD models as well. So like, say, industrial say, products. So maybe we want, of course, we want to scan 3D, but also we want to have textures, right?
Mm-hmm.
Yeah, I think we, in particular for 3DV, we want to invite many papers that do some combination of 3D geometry processing plus some, say, deformations or surface properties, or of course, deep learning stuff, of course. Yeah.
Thank you, Shohei. Thank you. And thank you also to everyone. I think with that, I know that Sylvia has to run to the other workshop. Thank you so much.
Thank you.
And also Shohei as well. So thank you, everyone. And congratulations to Julian and Gerard. I mean, it's the same team. Congratulations also to the SNT team for winning the second place. And thank you very much to Artec 3D for sponsoring this. And see you maybe next year in CVPR 22.
Yeah, thank you very much for this nice organization of workshop. It is really well organized. It is.
Thank
really,
you.
I mean, having organized workshops myself, this beats it by several levels.
It does take a full bus.
Yes,
the team is here.
You can really see that. And also the analysis of results, it's really useful. I think it's really cool. It would be really nice to have more participants, actually. It is really well done.
Indeed. Thank you very much. And thank you for acknowledging that. Thank you. Thank you, everyone.